Hello there, and welcome to Science for Sleep, where curiosity gets cozy, the universe lowers its voice, and even the largest things in existence are invited to move slowly enough for a tired mind to follow. Tonight, we're drifting towards something so large that the usual words start to feel a little underdressed. Not a planet, not a star, not a galaxy, not even a cluster of galaxies, but a structure so enormous that it stretches across a distance light itself needs more than 1 billion years to cross. It is called Quipu, and it may be the largest structure ever found in the cosmic web. Now, that is a sentence that deserves a moment to settle in. The largest structure ever found. It sounds like the kind of phrase someone might put on a poster with far too many exclamation marks, or perhaps on the side of a space museum exhibit, where a child is standing very still, trying to decide whether the universe is amazing or just showing off. But Quipu is not large in the way a mountain is large, or even in the way the Milky Way is large. It is large in a way that makes distance behave almost like a joke told by the cosmos, with a perfectly straight face. It is not a single solid object, of course. You could not bump into it like a wall. There is no glowing edge and no neat border, no sign saying, "Welcome to Quipu. Please keep your arms and legs inside the observable universe at all times." Instead, Quipu is a huge arrangement of galaxy clusters, a long uneven chain of matter spread through space, with dense knots and connecting strands, a little like a cosmic measuring cord tied with enormous beads of galaxies. And that name, Quipu, is part of the charm. A quipu was an ancient Andean recording system made from cords and knots, used to store information in a way that was both practical and beautifully physical. The cosmic quipu was named because its shape reminded astronomers of those knotted cords. Imagine for a moment the universe keeping a record of itself, not in ink, not on paper, not in a computer file that asks you to update it at the worst possible time, but in clusters of galaxies tied across the darkness like knots on a thread. It is a gentle image for something almost too large to picture. A cord made not of fibre, but of gravity. A set of knots made not by human hands, but by billions of years of matter gathering, falling, and pulling itself into shape. Before we wander too far into that enormous darkness, let me ask you something simple. Where are you listening from tonight? Are you tucked into a quiet room, looking at a ceiling that probably feels much closer than 1 billion light years? Are you listening late at night, early in the morning, or during one of those strange hours when the world feels half asleep and the kettle somehow sounds louder than usual? And if you look out from wherever you are, whether there are city lights, cloudy skies, a dark garden, or just the soft glow of a screen, can you imagine that beyond all of it, beyond the moon, beyond the planets, beyond the Milky Way, there are structures so vast that entire galaxies become little bright flecks inside them? If this gentle journey helps you settle, if it gives your mind something wide and quiet to rest against, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of science reach more sleepy travellers, more curious minds, and perhaps 1 or 2 people who came for the largest structure in the universe and stayed because the word Quipu is surprisingly pleasant to say. Quipu. It sounds a bit like a tiny bird, which is funny, considering it refers to something around 1.3 billion light years long. The universe does enjoy contrast. So settle in, let your shoulders loosen, and let the scale of ordinary life become gently smaller for a while. No rush is needed here. Quipu has taken billions of years to form, so we can take a few quiet minutes to approach it properly. To begin, it helps to remember that the universe is not sprinkled evenly with galaxies, like sugar across a table. That would be tidy, convenient, and slightly boring, which is probably why the universe chose something else. On the larger scales, galaxies gather into groups. Groups gather into clusters. Clusters arrange themselves into long filaments, and between those filaments lie immense empty regions called voids. The result is often called the cosmic web. It is one of the most useful ideas in modern astronomy, because it gives us a way to imagine the large-scale structure of everything we can see, not as a smooth fog, not as a random scatter, but as a vast network of strands and knots. If you have ever seen foam in a bath, or the delicate webbing inside a sponge, or even the pale branching lines of frost on glass, you already have a small household hint of the pattern. The universe, on its grandest scales, seems to prefer networks. Of course, the cosmic web is not made of soap bubbles or sponge fibres. It is made mostly of dark matter, ordinary matter, galaxies, gas, and gravity doing what gravity does best, which is slowly turning tiny early differences into enormous later consequences. In the young universe, matter was spread out almost evenly, but not perfectly evenly. There were slight variations, tiny regions with a little more density than others. Over billions of years, gravity amplified those small differences. Matter flowed toward matter, gas collected, stars formed, galaxies grew, clusters assembled, empty regions became emptier as matter drained away from them into denser regions. A faint pattern became a strong one, and the cosmic web emerged. That is already a very big story. But Quipu asks us to make the story bigger still. A galaxy cluster is one of the largest gravitationally bound structures in the universe. It can contain hundreds or even thousands of galaxies, along with enormous clouds of hot gas and a much larger halo of dark matter. These clusters are not gentle little neighbourhoods. They are enormous cities of galaxies, so massive that their hot gas shines in X-rays, and their gravity can bend the path of light itself. If galaxies are like houses, then galaxy clusters are the huge metropolitan regions of the cosmos, with traffic made of stars, gas, and invisible mass. Quipu is not just one of these clusters. It is a superstructure made from many clusters and connecting regions, spread across a staggering distance. The reported length of Quipu is over 400 megaparsecs. That number may sound clean and scientific, but it does not feel very friendly at first. A megaparsec is about 3.26 million light-years. So 400 megaparsecs is about 1.3 billion light-years. This means that if you could send a beam of light from one end of Quipu to the other, and if that beam had a very patient attitude, it would need more than 1 billion years to cross the structure. When that light began, Earth would not have had complex animals walking around. It would not have had forests with birds in them, no people, no cities, no telescopes, no one waiting for a laptop to finish updating at exactly the wrong moment. The light would still be travelling long before familiar life filled the planet. That is the kind of distance Quipu asks us to hold in our minds. And the mass is just as difficult to picture. Astronomers estimate Quipu contains around 200 quadrillion solar masses. One solar mass is the mass of our Sun. The Sun, already so massive that it holds the planets in orbit, becomes the tiny unit. Now multiply that by 200 quadrillion. It is a number so large that it almost stops being a number and becomes more like weather for the imagination. Not because it is vague, but because the human mind has not evolved to handle that scale comfortably. We are very good at understanding cups of tea, steps to the door, the weight of a blanket, the time it takes for toast to brown. We are less naturally prepared to picture a mass written as a 2, followed by 17 zeros. That is not a failure of imagination. It is just that our imagination was built on Earth, under a familiar sky, with feet on the ground and snacks in cupboards. Still, we can approach the number gently. The Milky Way, our home galaxy, contains hundreds of billions of stars and a great deal of dark matter. It is already immense. Quipu is estimated to be vastly more massive than the Milky Way. Not 10 times, not 100 times, but on a scale where our galaxy becomes one small part of the broader cosmic accounting. This does not make the Milky Way unimportant. It is still our home, our address in the universe, the place where every person who has ever lived has looked up from. But it does remind us that cosmic size comes in layers, and every time we think we have reached the top shelf, astronomy quietly brings in a taller ladder. One of the reasons Quipu matters is that structures this large can affect the way we interpret the universe around them. A superstructure of galaxy clusters is not just a pretty pattern on a map. It has gravity. It contains matter. It can influence measurements of cosmic expansion. It can leave subtle imprints on the cosmic microwave background, the ancient leftover light from the early universe. It can affect how we understand the distribution of matter nearby. In other words, Quipu is not just large for the sake of being large, like a cosmic novelty item. It is large enough that astronomers have to pay attention to it when they're trying to make accurate maps and measurements of the universe. That is a wonderful thing about science. A discovery can be both beautiful and inconvenient. It can inspire awe and also make researchers sharpen their pencils. Quipu is not merely a headline saying, "Look, a huge thing." It is a reminder that the universe is structured, uneven, and full of local features that must be understood if we want to measure the whole. It is like trying to understand the shape of a landscape while standing near a mountain range. The mountains matter. They affect what you can see, how distances appear, where shadows fall, and how the map should be drawn. Quipu is a mountain range of the cosmic web, except the mountains are galaxy clusters, and the landscape is hundreds of millions of light years across, slightly harder to pack for, admittedly. The discovery also sits inside a long tradition of cosmic mapping. For centuries, humans have been trying to draw the world beyond us. First we mapped the stars as patterns in the sky, then the planets as wandering lights, then nebulae, galaxies, clusters, superclusters, walls, filaments, voids, and larger structures. Each map changes the feeling of where we are. The first maps placed Earth under a dome of stars. Later maps placed Earth around the Sun. Then the Sun became one star in the Milky Way. Then the Milky Way became one galaxy among billions. Then galaxies became part of a web. And now, with structures like Quipu, even the web has features so huge that they deserve names of their own. There is something deeply calming about that, at least when you let the scale arrive slowly. Your worries do not disappear, of course. A cosmic superstructure does not answer emails, wash dishes, or find the missing sock that somehow escaped from the laundry, as if it had a small private spacecraft. But it can change the room around those worries. It can place them inside a larger frame, the same universe that contains your busy day, your tired thoughts, and your little rituals before sleep also contains Quipu, a vast knotted arrangement of galaxy clusters spread across 1 billion light years. Both are real. The small and the enormous share the same existence. The cup beside your bed and the largest known structure in space both belong to the same story. What makes Quipu especially interesting is that it is found in the nearby universe, at least by cosmological standards. Nearby, in astronomy, is a very generous word. It can mean hundreds of millions of light years away, which is a bit like saying the shop is just around the corner when the corner is on another continent. But compared with the full observable universe, which stretches tens of billions of light years in every direction we can see, Quipu is part of the relatively local cosmic environment. It is not next door in any ordinary sense, but it is close enough to be mapped in meaningful detail using galaxy clusters and X-ray observations. That makes it useful. The nearby universe is the region where astronomers can study large-scale structure with better clarity, where the cosmic web is not just an idea but something that can be traced. And here we come to the quiet detective work behind the discovery. Quipu was identified through a survey that used galaxy clusters seen in X-rays. That is important because galaxy clusters contain extremely hot gas, heated to millions of degrees, which shines in X-ray light. Our eyes cannot see X-rays, thankfully, because that would make both astronomy and a sunny day rather uncomfortable. But space telescopes can detect them. By studying X-ray bright clusters, astronomers can trace some of the densest knots in the cosmic web. These clusters act like signposts. Connect enough signposts and patterns begin to appear, some are modest. Some are familiar, and then, sometimes, a pattern stretches farther than expected and becomes something record-breaking. There is a nice sleep-friendly lesson hidden in that method. Quipu was not found by simply staring at a pretty patch of sky and noticing a giant glowing rope. It was found through careful mapping, through data, through comparing distances, positions, masses, and relationships. The largest structure ever found did not announce itself with a dramatic flash. It was assembled in human understanding, piece by piece, cluster by cluster, like someone slowly realizing that the scattered beads on a dark floor are actually part of one very long necklace. Astronomy often works that way. The universe gives us clues, not labels. We provide the patience. That patience matters because size alone can be tricky in cosmology. When astronomers talk about a structure like Quipu, they are not usually saying it is a single object in the same sense that a planet or star is a single object. It is not solid. It is not bound together in the simple, tidy way the Earth is bound together. Some parts may be gravitationally connected in complex ways, while the expansion of the universe also plays a role on the larger scales. These enormous superstructures are patterns in the distribution of matter, meaningful patterns, measurable patterns, but not objects you could place on a shelf. This is why the word structure is so useful. It lets us describe shape, connection, and concentration without pretending the cosmos has built a physical bridge with railings and a snack machine at the midpoint. Quipu is part of that bigger conversation about what counts as a cosmic structure. It reminds us that the universe is not simply full of things, it is full of relationships between things. A galaxy is made meaningful by its stars. A cluster is made meaningful by its galaxies. A superstructure is made meaningful by its clusters and filaments. And the cosmic web itself is made meaningful by the contrast between crowded regions and vast voids. Space is not equally busy everywhere. Some places are cosmic cities, some are quiet deserts, some are long roads between the cities. Quipu is one of the largest road and city systems we have ever mapped. As you rest with that image, it may help to picture Quipu not as a bright object blazing in the night, but as a pattern revealed by patient measurement. If you looked toward its region of the sky with ordinary eyes, you would not see a huge cord stretched across the heavens. You might see stars in our own galaxy, perhaps a familiar constellation, perhaps nothing special at all. The largest structure in the universe is hidden, not because it is faint in every sense, but because it is too spread out, too deep, and too far beyond everyday perception. It needs instruments. It needs catalogues. It needs redshifts, X-rays, and careful statistical work. Sometimes the biggest things are not obvious. Sometimes they are so large that you have to step far back in thought before they appear. That is true in ordinary life as well, in a much smaller way. A single day can feel random while you're inside it. A conversation here, an errand there, a message you forgot to answer, a cup of tea that went cold because you were distracted. But step back far enough, and patterns appear. Habits, seasons, friendships, the routes your life takes without asking permission first. The universe is different in scale, but the principle is familiar. Close up, there are galaxies. Farther back, there are clusters. Farther still, there is Quipu. The discovery also gives us a fresh way to think about our address in the cosmos. We live on Earth, orbiting the Sun. The Sun sits in the Milky Way. The Milky Way belongs to the Local Group, a small gathering of galaxies that includes Andromeda. The Local Group sits in a larger environment connected to the Virgo cluster and the broader Laniakea region. Beyond that, the cosmic web stretches in all directions, with superclusters, filaments, walls, and voids. Quipu is not where we live in the immediate sense, but it belongs to the same nearby cosmic neighbourhood map, the same grand attempt to understand how matter is arranged around us. It is part of the landscape beyond our doorstep, if your doorstep happens to be measured in hundreds of millions of light years, which would make receiving parcels very inconvenient. There is another reason Quipu feels so compelling. it presses gently against a question cosmologists care about very much. How lumpy should the universe be at the larger scales? According to modern cosmology, the universe should become more uniform when viewed on sufficiently enormous scales. That does not mean there are no structures. It means that if you zoom out far enough, no region should be wildly special compared with another. Large structures can exist, but they need to fit within the expectations of cosmic evolution. Quipu, according to the researchers, appears to be compatible with the standard cosmological model, because simulations can produce similar superstructures. That matters. It means Quipu is not necessarily a sign that everything is broken. It may be a spectacular example of what gravity can build in a universe seeded with early density fluctuations. The universe can be surprising without being impossible. And honestly, that is a soothing thought. Not every astonishing discovery has to overturn reality. Sometimes it deepens it. Sometimes it says, here is what the known laws can do when given enough time, enough matter, and enough room. Gravity, with no hurry at all, can gather galaxies into clusters, clusters into chains, chains into huge knotted superstructures, until a map of the sky begins to resemble an ancient chord used for counting. No drama required. Just physics, patience, and a great deal of space. Still, even if Quipu fits within our models, it changes the way we feel those models. A universe made of equations can seem cold from a distance. But a universe with named structures, with knots and filaments and enormous connected forms, becomes easier to imagine as a place. Not a place we can walk through, of course. You cannot book a quiet weekend in Quipu, although the travel time would certainly encourage relaxation. But it becomes a feature in the landscape of thought, a landmark, a reminder that the cosmos is not just expanding emptiness, it has texture. Texture is a good word for this. The universe has texture the way fabric has texture, with threads crossing, bunching, thinning and tightening. Quipu is one of the largest textures we have noticed, and like a piece of fabric, it tells us something about how it was made. Pull on one thread, and you learn about the weave. Study one superstructure, and you learn about dark matter, galaxy cluster formation, cosmic expansion, and the conditions of the early universe. A structure that seems distant and almost unreal becomes a tool. It helps us test whether our picture of the universe is accurate. It helps us correct observations. It helps us understand what kind of cosmic neighborhood we occupy. That is where the story becomes more than scale. Enormous size catches attention, but meaning comes from what size does. Quipu is so large that it may influence measurements astronomers use when they study the universe as a whole. It can affect observations of the cosmic microwave background through subtle changes caused as light passes through evolving gravitational fields. It can contribute to the way matter flows locally. It can matter for estimates of cosmic parameters. None of this makes Quipu a monster lurking in space. It is not dangerous. It is not coming for us. It is not going to drift into the solar system and rearrange the furniture. It is far too vast and diffuse for that kind of behaviour. But it is important because precision astronomy depends on knowing what lies between us and the deeper universe. The foreground matters. The local cosmic landscape matters. The big nearby knots in the web matter. Maybe that is why this discovery feels so fitting for a quiet night. It is both enormous and subtle. It is grand enough to stretch the mind, but it was found through careful attention to small signals and patient cataloguing. It is not a firework, it is a pattern, and patterns are friendly companions for sleep. The mind can follow them without being jolted. A galaxy cluster here, a connecting filament there, a dense central region, a long extension, another knot, another cluster. A chord across the dark. So tonight, as your room stays still around you, we begin with the simple fact that the universe has made something vast enough to challenge ordinary imagination, yet structured enough to be named after knots on a chord. Quipu is not just a record holder. It is a clue about how matter gathers, how gravity writes across space, and how the nearby universe is arranged in ways we're only just learning to map clearly. It asks us to think beyond galaxies as lonely islands and instead picture them as bright towns along immense roads, gathered into provinces of matter separated by quiet voids. And from here, the natural question becomes not just how vast Quipu truly is, but how it was ever discovered in the first place. The trail begins not with a single photograph, not with a telescope catching one enormous glowing shape in the night, but with a much quieter kind of discovery. The sort that arrives through catalogues, coordinates, redshifts, repeated measurements, and patient people looking at dots until the dots begin to confess that they are not random after all. Quipu was not found because it flashed in the sky like a sign. It was found because astronomers learned how to trace the heaviest knots in the nearby universe, and then noticed that some of those knots were lined up in a way that was far too impressive to ignore. This is one of the strange things about the largest structures in the cosmos. You might imagine that the biggest things would be the easiest to see. After all, if something is huge, surely it should stand out. A mountain stands out from a field. A whale stands out in a swimming pool, which is not a recommended arrangement for anyone involved. But in astronomy, size can hide itself. Something can be so spread out across the sky, so deep in distance, and so mixed with other objects along the line of sight that you do not see it as one thing at first. It is like standing inside a city and trying to understand the whole road map from one street corner. You can see buildings, you can see traffic lights, you can see someone carrying a bag of groceries with great seriousness. But the shape of the city only appears when you map it from above. Astronomers had to do something similar with Quipu. They had to step back, not with their bodies of course, because stepping back 1 billion light years is inconvenient before breakfast, but with data. They needed a way to map the large-scale matter distribution of the nearby universe, not just one bright galaxy here or one famous cluster there. They needed a wide survey, one that covered most of the sky and included reliable distances. Most importantly, they needed good traces of where the greatest concentrations of matter were hiding. That is where galaxy clusters become useful. A galaxy cluster is not just a crowd of galaxies. It is a massive structure held together by gravity, containing galaxies, dark matter, and huge amounts of extremely hot gas. That gas is important because it shines in X-rays, not visible light, not the soft glow you might see through a backyard telescope, but high-energy radiation produced by gas heated to millions of degrees. This gas fills the space between the galaxies in a cluster, and because it is so hot, it gives astronomers a way to find clusters across enormous distances. In a sense, the clusters breathe in X-rays. Not literally, of course. Space is not gently exhaling into a detector like someone fogging up a window, but the idea is close enough for a sleepy mind. The hot gas marks the cluster. The cluster marks a heavy knot in the cosmic web. And enough knots, carefully placed, can reveal the thread. For Quipu, astronomers use galaxy clusters detected in X-rays as signposts of mass. This matters because galaxies alone can sometimes be misleading. Galaxies are bright, beautiful, and numerous, but they can be affected by selection effects, brightness limits, dust, and the simple difficulty of collecting complete information across the whole sky. Clusters, especially X-ray detected clusters, are different. They tend to sit in the deepest gravitational wells. They are like the large towns and cities of the cosmic landscape. If you're trying to understand the shape of a country, you might start by marking its major cities. If you're trying to understand the nearby cosmic web, you can start by marking its galaxy clusters. The survey behind this work is called CLASSIX. It is built from X-ray cluster data based on the Rosat All-Sky survey, which mapped the sky in X-rays. CLASSIX combines major cluster surveys from both hemispheres, including the Southern Reflex survey and the Northern Norris survey, giving astronomers almost all-sky coverage. That all-sky part is not just a technical detail, it is crucial. If you only look at a narrow strip of sky, You might find part of a structure but miss its true length. You might mistake a long filament for a short one simply because your window was too small. It would be like peering through a letterbox and trying to measure an elephant. You may learn something, but you should not be too confident about the tale. With an almost all-sky X-ray cluster sample, astronomers could search for large matter concentrations in a more complete way. They focused on a region of the nearby universe between roughly 130 and 250 megaparsecs away. In light years, that means hundreds of millions of light years from us. Nearby, by cosmic standards, is a very relaxed word. It does not mean you could pop over for the weekend. It means that compared with the full observable universe, this region is close enough for detailed mapping and far enough to contain enormous structures that help shape our local cosmic environment. The method begins with knowing where the clusters are. Each cluster has a position on the sky, but that alone is not enough. The sky is two-dimensional to our eyes, like a ceiling with lights pinned on it, but the universe has depth. Two clusters may appear close together from our viewpoint while actually being very far apart, one in front of the other, like two lamps lined up along a hallway. To build a three-dimensional map, astronomers need distances. They get those distances through redshift, the stretching of light caused by the expansion of the universe. The farther a galaxy cluster is, generally speaking, the more its light has been stretched toward the red end of the spectrum. Redshift is not just a number, it is a cosmic distance clue. Once the positions and redshifts are known, the dots become a three-dimensional pattern. At first, it may still look like a mess, a galaxy cluster here, another there, a handful farther away, a dense region, a thin region, a confusing patch near the Milky Way where dust and stars get in the way. But the human eye and, more importantly, careful algorithms can begin to ask a simple question. Which clusters belong together as part of a larger structure? This is where linking comes in. Imagine looking at beads scattered on a table. Some beads sit close enough that you might thread them together. Others are too far away and probably belong to a different necklace. If you choose a very short thread, you will connect only tight little groups. If you choose a very long thread, you might connect almost everything into one unhelpful mess, which is exactly how some drawers full of cables behave when left unattended. Astronomers use a more disciplined version of this idea. They define linking lengths and density thresholds to decide which clusters are connected as part of a superstructure. The goal is not to force the universe into a pattern, but to identify where the matter distribution has clearly evolved away from a random background. For the Quipu study, the researchers searched for major superstructures containing at least 20 classics cluster members and showing significant overdensity in the cluster distribution. This means they were not looking for tiny associations or loose coincidences. They were looking for the largest, most prominent features, the kind that could matter for cosmology and for our understanding of the local large-scale structure. Among the 5 most prominent superstructures they found, one stood out. It stretched across the map as a long filament with side branches. It was not merely large, it was enormous. Its measured length was about 428 megaparsecs, which is around 1.4 billion light-years depending on the conversion used. That was Quipu. There is something wonderfully understated about this moment. After all the data, the coordinates, the redshifts, the X-ray measurements, the completeness checks and the linking analysis, the largest known cosmic structure appears as a pattern in a map. Not with thunder, not with a trumpet. Just a long arrangement of clusters, quietly becoming obvious. The researchers even noted that Quipu is readily visible by eye in the sky map of clusters within the target distance range. That detail is rather delightful. After all that careful machinery, there it is, the giant cord in the data, visible once you know how to look. Its shape helped give it its name. Quipu resembles a long filament with smaller side filaments, like a cord with knots and hanging threads. The original quipus of the Andes were used for recording information through knots on cords, and the cosmic quipu looked enough like that ancient system that the name fit. It also carried a connection to Chile, where many of the cluster redshifts had been obtained through observations at the European Southern Observatory, so the name is not just decorative, it reflects shape, history, and the human side of astronomy. A researcher sees an ancient recording device in a museum, remembers the knotted form, and later the universe presents a similar form made of galaxy clusters. Science is full of equations, but it is also full of people making associations, naming things, and quietly enjoying when the cosmos offers a good metaphor without being asked. The work did not stop with the cluster map. A good discovery becomes stronger when it can be checked in more than one way. So the researchers compared the superstructures traced by X-ray clusters with the distribution of galaxies in the 2-mass redshift survey. This is an important step because if the clusters are truly tracing large-scale matter, the surrounding galaxy distribution should show related overdensities, and it did. The galaxy maps showed the same broad features. Quipu was not just a chain of X-ray clusters floating in a statistical daydream. It corresponded to a real enhancement in the galaxy distribution as well. In simpler terms, when astronomers looked for the galaxies around the cluster-defined structure, the galaxies agreed. The towns were where the cities suggested they should be. That kind of agreement is comforting in observational astronomy. The universe is difficult to measure, and every method has its own quirks. X-ray surveys detect hot gas in clusters. Infrared galaxy surveys trace starlight from galaxies, often with less trouble from dust than visible light. Redshift measurements give distance. Simulations test whether similar structures can arise in a universe governed by known physics. When different lines of evidence point toward the same pattern, confidence grows, not because the universe has become easy, but because the clues start to hold together. Still, the map was not perfect, because no map of the universe is perfect. One of the awkward features astronomers must deal with is the zone of avoidance. That sounds like a place in a fantasy novel where no one should open the gate after dark, but it is actually the region of the sky blocked by the disk of our own Milky Way. Our galaxy is filled with stars, gas and dust, and when we look through its crowded plane, distant galaxies and clusters become harder to see. It is like trying to study a landscape through a dirty window while someone keeps walking in front of it holding a lamp. The zone of avoidance hides part of the extragalactic universe from our view. Quipu runs close to this difficult region, and the researchers noted that it may extend farther into or beyond the zone of avoidance. In the north, it reaches the obscured region, and there are hints of cluster concentrations on the other side. In the south, it lies close to the Vela supercluster region. This does not mean Quipu is uncertain in its main form. It means its full extent may still be partly hidden by the Milky Way's foreground. That is a very cosmic kind of frustration. The largest structure ever found, and our own galaxy is standing partly in the way, like a tall person at the front of a cinema. This is also a reminder that cosmic maps are always improving. What we call the largest known structure today is not necessarily the largest structure that exists. It is the largest one we have identified with the data and methods currently available. The universe has no obligation to make its record holders easy to find. Better surveys, deeper observations, and improved coverage of obscured regions may reveal that Quipu is longer, connected differently, or accompanied by other structures of similar scale. Discovery is not a single door opening. It is more like a hallway, and every opened door reveals a few more doors, which is exciting unless you're just trying to find the bathroom at night. The astronomers also compared their findings with simulations based on the standard model of cosmology, often called lambda CDM. These simulations allow researchers to ask whether structures like Quipu are expected in a universe with dark matter, dark energy, ordinary matter, and gravity evolving from the early universe. This is important because an enormous structure can raise eyebrows. If a structure is too large, too massive, or too unlikely, it might challenge the model. But the researchers found similar superstructures in simulations, which suggest that Quipu is not a cosmic mistake. It is extraordinary, but not impossible. The universe can grow very large patterns while still following the rules we think it follows. That may sound less dramatic than saying Quipu breaks cosmology, but it is actually more useful. A discovery does not need to break everything to matter. Often, the most valuable discoveries refine our understanding. They show us what the rules look like when played out at full scale. Gravity can be patient. Dark matter can provide the scaffolding. Ordinary matter can fall into place. Galaxies can form. Clusters can gather. Filaments can stretch. And after billions of years, a structure like Quipu can appear in the nearby universe, long enough to make the Milky Way seem like a small bright bead on a much larger map. The discovery also highlights how modern astronomy is not only about looking deeper into space, but also about looking more completely around us. There is a temptation to think that the most exciting discoveries are always the farthest away, at the edge of the observable universe, where galaxies are young and light has travelled for most of cosmic history. Those discoveries are indeed extraordinary, but the nearby universe still has secrets. Our own cosmic neighbourhood is not fully mapped. Its great walls, filaments, superclusters, voids, and hidden regions still need careful attention. Quipu was found not at the edge of all sight, but in the relatively nearby large-scale structure, the region whose matter concentrations can influence local measurements and motions. Sometimes, the universe does not need to whisper from the beginning of time. Sometimes it can surprise us from the neighbourhood. Finding Quipu required a combination of old and modern tools. The Rosat All-Sky survey was carried out decades ago, yet its X-ray data continue to support major discoveries when combined with follow-up observations, redshift measurements, improved catalogues, and new analysis. There is something reassuring about that. Science is not always a clean sequence where old data are thrown away and replaced by shiny new data like phones in a drawer. Sometimes old observations become part of a longer conversation. A survey maps the sky. Years pass. More redshifts are collected, methods improve, questions change. Then, suddenly, the old map helps reveal something enormous. The data were waiting, not asleep exactly, but perhaps resting patiently until the right question came along. And this is a good place to notice the human patience inside the discovery. Every point on the map represents work. Someone had to detect the cluster, confirm it, measure its redshift, estimate its X-ray luminosity, understand the survey limits, and place it correctly in a catalogue. One cluster is a data point. Many clusters become a pattern. Enough patterns become a new view of the universe. Large discoveries often depend on thousands of small, careful actions, most of them not glamorous, many of them repetitive, all of them necessary. The largest structure ever found was not discovered by one dramatic glance through a telescope. It was assembled through discipline. That makes the story feel almost gentle. Quipu is huge, but the method of finding it was careful, incremental, almost tidy. Gather reliable cluster data, map distances, search for overdensities, link clusters into candidate structures, check the galaxy distribution, compare with simulations, consider observational effects, name the shape, publish the result. There is a calmness in that chain of work, a rhythm of evidence building until the conclusion becomes hard to avoid. The universe placed a vast cord of clusters across the nearby cosmos, and astronomers followed the knots. As we move through this story, it helps to keep one thought close. Quipu is not a single object in the everyday sense. It is not like discovering a new planet or a new moon. It is a superstructure, a large-scale arrangement in the distribution of matter. Its boundaries depend on how clusters are linked and how overdensities are defined. That does not make it unreal. A mountain range is real even if its exact beginning and ending can be debated. A city is real even if its suburbs fade gradually into the countryside. A cloud is real even though its edges are soft. Quipu is real as a cosmic structure because the matter distribution shows a coherent, measurable, meaningful pattern. It is a feature of the universe's large-scale landscape. Once that becomes clear, the discovery becomes even more interesting. Astronomers did not simply find a big thing. They found a way the universe organizes itself. They identified one of the largest known examples of the cosmic web's architecture, using galaxy clusters as the heavy markers of the pattern. It is as though the universe drew a very faint map in matter, and X-ray astronomy helped trace the ink. So when we ask how astronomers found Quipu, the answer is both simple and layered. They found it by looking for the biggest knots in the nearby universe. They used X-ray galaxy clusters because clusters trace deep wells of mass. They measured distances through redshifts. They built an almost all-sky three-dimensional map across a particular range of cosmic distance. They linked clusters into superstructures and looked for significant overdensities. They compared the results with galaxy surveys and simulations. And in that careful process, one structure stretched out farther than all the others, long, branched, massive and shaped, enough like an ancient knotted cord to earn the name Quipu. From the quiet room where you're listening, that process may feel very far away. There are no X-ray catalogues on your bedside table, probably. No cluster redshift survey tucked under the pillow. But the basic act is familiar. It is the act of noticing that separate things may belong together. Stars become constellations in the human eye. Days become memories in the mind. Dots become maps. Clusters become a cosmic chord. The universe offers scattered clues, and slowly, carefully, we learn to read them. To understand what Quipu really is, it helps to gently rearrange the way we picture the universe. Most of us first learn about space as a collection of separate things. A planet here, a moon there, a star at the centre of a solar system, a galaxy filled with stars, maybe another galaxy nearby. It is a natural way to begin, because our eyes and our minds like objects. We like things with edges. A cup has an edge, a pillow has an edge, a biscuit has an edge, at least until someone in the room makes a small but decisive scientific observation and eats it. Space, though, becomes harder to understand when the things grow so large that the edges become soft, uneven, and sometimes more a matter of measurement than of walls. Quipu belongs to that larger, softer category. It is not an object like a planet. It is not even an object like a galaxy. It is a cosmic superstructure, which means it is a vast arrangement of matter, marked by galaxy clusters and connected regions, spread across such a large volume of space that we understand it best as part of the universe's large-scale pattern. That distinction matters because if we imagine Quipu as one solid thing, we get the wrong picture immediately. There is no surface to land on, no outside shell, no single glowing body sitting in space like a giant cosmic loaf of bread, which would at least make the universe smell interesting. Quipu is more like a huge region where matter is unusually concentrated compared with the cosmic average. It is made of many pieces that are related by position, density, and large-scale structure. Those pieces include galaxy clusters, groups of galaxies, filaments, and surrounding matter. The structure is meaningful because these pieces are not scattered randomly. They form a connected pattern, one that can be traced across hundreds of megaparsecs. It is a map feature in the cosmic web, not a single self-contained object. The easiest way to build up to that idea is to start small, or at least small by the very generous standards of astronomy. Earth is a planet. It orbits the Sun. The Sun is a star. It sits inside the Milky Way, which is a galaxy containing hundreds of billions of stars, along with gas, dust, planets, stellar remnants, dark matter, and a great many places where no one has ever had to remember a password. The Milky Way is already huge. Light takes about 100,000 years to cross it from one side to the other. That is so long that if a beam of light started on one side of the Milky Way when early humans were living on Earth, it might only now be reaching the other side. And yet, in the story of Quipu, a galaxy is not the largest unit. It is more like a bright building block. Galaxies often gather in groups. Our own Milky Way belongs to the local group, a modest collection of galaxies that includes Andromeda, the Triangulum Galaxy, and many smaller dwarf galaxies. The local group is held together by gravity. It is not perfectly still, of course. Nothing in the universe has much interest in sitting completely still. The Milky Way and Andromeda are moving toward each other and will eventually merge in the distant future. But even this local family of galaxies is still small compared with what comes next. Above groups we find galaxy clusters. These are much larger gatherings, sometimes containing hundreds or thousands of galaxies. They also contain enormous amounts of hot gas between the galaxies and a much larger amount of dark matter surrounding the whole system. Galaxy clusters are among the largest structures that are clearly gravitationally bound. This means their gravity is strong enough to hold them together as systems. A cluster is not just a crowd seen from far away. It is a physical association, a deep gravitational basin where galaxies, gas and dark matter are all part of the same larger structure. If the local group is a quiet village, then a galaxy cluster is a major city with many districts, a lot of traffic, and probably at least one galaxy that would complain about parking if galaxies had meetings. These clusters become especially useful when we want to understand the cosmic web, because they mark the densest knots. The universe is not filled evenly with matter. On very large scales, matter forms a network. There are dense knots where clusters sit. There are long filaments connecting those knots. There are sheet-like walls in some regions. Between them lie huge voids, regions with far fewer galaxies. This large pattern is what astronomers call the cosmic web. It is not a decorative phrase. It describes the real large-scale arrangement of matter shaped by gravity over billions of years. A cosmic superstructure is one of the very large features within this web. It can include several galaxy clusters and the filaments that connect them. It can stretch across distances much larger than an individual cluster. It may not be fully gravitationally bound as a single object, especially when it reaches hundreds of millions or more than 1 billion light-years in size. That point is important. Gravity pulls matter together, but the universe is also expanding. On smaller scales, gravity can win clearly. Earth holds onto the moon, the sun holds onto the planets, a galaxy holds onto many stars, a cluster holds together its galaxies and gas. But on the larger scales, expansion becomes part of the story. A superstructure can be a real pattern in the matter distribution, without being one tidy object that will collapse into a single thing. This is why the word superstructure is useful. It gives astronomers a way to describe something larger than a cluster and more complicated than a simple supercluster. It says, here is a huge connected overdensity in the cosmic web. Here is a region where matter is arranged in a coherent pattern. Here are clusters, filaments, and surrounding galaxies that belong together in the map. It does not say that Quipu is a single solid body. It does not say that every part of it is holding hands gravitationally in the same neat way. It says that the universe has arranged matter into a vast identifiable feature, and that feature is large enough, massive enough, and structured enough to study as one of the major landmarks of the nearby universe. The word overdensity may sound a little dry, but it is one of the most important ideas here. Imagine sprinkling oats across a table, because apparently astronomy can happen before breakfast. If the oats were spread evenly, every part of the table would have roughly the same amount. But if some regions had clumps and other regions were nearly empty, you would have overdense and underdense areas. The universe works in a far more complex way, of course, and with fewer oats, unless something has gone very wrong at the telescope. But the basic idea is similar. A cosmic superstructure is a large region where the density of matter, traced by galaxies and clusters, is higher than average. A void is the opposite, a region where the density is lower than average. Quipu is a superstructure because it is a huge connected overdensity traced by galaxy clusters. Those clusters are not just decorative markers, they are indicators of deep gravitational wells. They tell astronomers where large amounts of matter have gathered. Since much of that matter is dark matter which does not shine, astronomers need tracers. Galaxies trace matter. Hot gas in clusters traces matter. X-ray emission traces the hot gas. Cluster catalogues trace the knots. Through all of this, the invisible structure of the universe becomes indirectly visible. It is a little like learning the shape of a person under a blanket by watching where the blanket rises and falls. You cannot see everything directly, but the shape still leaves clues. Dark matter is central to this story, even though it remains unseen. Ordinary matter, the kind that makes stars, planets, tea mugs and sleepy listeners, makes up only a small fraction of the universe's total matter and energy. Dark matter does not emit light, absorb light, or reflect light in a way telescopes can detect directly. But it has gravity. That gravity helped shape the cosmic web. In the early universe, small density variations acted like seeds. Dark matter gathered first, forming a kind of invisible scaffolding. Ordinary matter fell into those gravitational wells, gas collected, stars formed, galaxies appeared, and over time the web became visible through the galaxies and clusters that formed along the dark matter structure. So when we look at Quipu, we are not only looking at where galaxies are, we are looking at the visible sign of a deeper gravitational pattern. The galaxy clusters are like lamps placed along roads, whose foundations are made mostly of dark matter. The lamps do not create the roads, but they show us where the roads must be. That is why a superstructure is not only a collection of visible galaxies, it is also a clue to the matter we cannot see directly. There is another subtle point here. A cosmic superstructure does not need to have a perfectly sharp border. That can feel strange, because many everyday objects do have clear boundaries. Your bed ends where the floor begins, your room ends at the wall, a sandwich ends when regrettably there is no sandwich left. But many natural structures have softer edges. A forest thins gradually into open land, a storm system fades at the edges, a city becomes suburbs, then countryside. Where does it exactly stop? You can draw a line on a map, but the real transition is gradual. Quipu is more like that. Astronomers define it using data, thresholds, linking lengths, and density patterns. The structure is real, but its exact border depends on the method used to trace it. This does not make the discovery weak, it makes it honest. Science often works with categories that have useful boundaries rather than perfect ones. A mountain range is real even if people can debate which foothills belong to it. A river system is real even if the smallest streams are hard to classify. A superstructure is real because the matter distribution shows a coherent pattern, but its edges are not like the edge of a marble. They are measured, not touched. Quipu also helps us see the difference between a structure and a bound object. The Earth is bound together. If you could somehow turn off cosmic expansion, Earth would not notice very much, because its own gravity and internal forces dominate. A galaxy is bound together. A galaxy cluster is bound together, but a structure more than 1 billion light-years long is not necessarily bound as one single future object. Some parts may remain associated, while other parts may separate over cosmic time as the expansion of the universe continues. In fact, very large superstructures can be temporary arrangements in the long-term story. They exist now as meaningful patterns, but they are not guaranteed to behave like one permanent object forever. That idea may sound a bit unsettling at first, but it is actually helpful. It prevents us from imagining Quipu as a giant galaxy cluster that simply has not finished packing itself. Instead, Quipu is a present-day feature of the large-scale universe. It is something we identify in the arrangement of matter at this stage of cosmic history. It tells us how matter has clustered so far. It tells us how the nearby universe is shaped. It may influence observations and measurements. It is real, but real in the way a weather system is real, or a continent's mountain chain is real, or a city's road network is real. It is a pattern with physical causes and measurable effects, not a single hard-edged object drifting through space. This is one reason cosmic language can be tricky. Words like structure, superstructure, supercluster, wall, filament, and void sound simple, but each carries a technical meaning. A filament is a long, thread-like concentration of matter, often connecting clusters. A wall is a broader sheet-like arrangement. A void is a large underdense region with fewer galaxies. A supercluster is a large association of galaxy groups and clusters. A superstructure can refer to an even broader connected arrangement found in the large-scale distribution of matter. Quipu has been described as a superstructure because it is identified through clusters linked into a massive extended pattern, larger than ordinary superclusters and important for mapping the nearby cosmos. The scale of Quipu makes it especially remarkable. At more than 400 megaparsecs in length, it stretches across a region so large that even light takes around 1.3 to 1.4 billion years to cross it, depending on the exact conversion and how the structure is measured. This scale is not just larger than the Milky Way, it is larger than galaxy clusters, larger than many previously known walls and superclusters, and large enough to be compared with the biggest entries in the catalogue of cosmic structures. Yet the main point is not only that Quipu is long. The main point is that it belongs to a pattern of matter that can be traced and tested. The researchers who identified it also found several other major superstructures in the same nearby distance range. Together, these superstructures contain a large share of the galaxy clusters in that surveyed volume. That is important because it tells us the nearby universe is not merely sprinkled with clusters in isolation. A significant fraction of the clusters belong to major superstructures. The densest objects are not just scattered like loose buttons in a drawer. Many of them are arranged along larger threads and concentrations. The nearby universe has a geography. Geography is a useful word, even though we are not talking about land. On Earth, geography helps us understand mountains, rivers, plains, coasts, and cities. In the universe, large-scale cosmic geography helps us understand clusters, filaments, walls, voids, and superstructures. Quipu is a feature in that geography. It is a huge cosmic region with a particular shape and mass distribution. It may affect how matter moves nearby. It may influence how light from the deeper universe is slightly altered as it travels through changing gravitational fields. It may matter for precision cosmology, where tiny effects must be accounted for carefully. A superstructure this large is not just something to admire. It is something that must be included in the map if the map is meant to be accurate. This brings us to a very practical question. Why should astronomers care about cosmic superstructures at all? One answer is that they help test cosmology. Our standard model says that the universe began in a hot, dense state, expanded, cooled, and developed structure from tiny early density fluctuations. Dark matter played a major role. Dark energy now affects the expansion. Gravity shaped matter into a web. If we observe structures that match what simulations predict, that supports the model. If we found structures that were too large or too common to explain, that might suggest something is missing. Quipu, as extraordinary as it is, appears to be within what simulations can produce. That makes it a major example of a large-scale structure, not necessarily a contradiction. Another answer is that superstructures affect the environment of galaxies. A galaxy in a dense region may evolve differently from a galaxy in a void. It may interact more often. It may lose gas. It may have its star formation affected by the hot gas around clusters or by gravitational encounters. The environment matters. Just as a person's life is shaped in part by their neighbourhood, a galaxy's life can be shaped by its cosmic surroundings. A galaxy in a cluster is not living the same quiet existence as a galaxy in a sparse field. A superstructure gives astronomers a larger environmental context. It says not only where the galaxy is, but what wider cosmic system surrounds it. Quipu also reminds us that the universe has many levels of belonging. The Sun belongs to the Milky Way. The Milky Way belongs to the local group. The local group lies in a larger flow of galaxies and clusters. Nearby superstructures shape the regional landscape. And all of this sits inside the expanding universe. Nothing is truly isolated. Even regions that seem lonely are part of the larger pattern. A void is defined by the matter around it. A filament is defined by the emptier regions beside it. A cluster is fed by filaments. A superstructure is traced by clusters. The cosmic web is a story of relationships. That does not mean every relationship is simple. In fact, cosmic superstructures can be messy. They may branch. They may overlap in projection. They may connect near obscured regions of the sky. Their apparent shape can depend on the distance range being studied. They can be affected by survey limits. They can be partly hidden behind the Milky Way's dusty plain. Astronomers have to correct for all of this. They have to ask whether a feature is real, whether it is complete, whether it continues beyond the observed region, whether it is being distorted by our viewpoint. Cosmic mapping is not just drawing lines between dots. It is careful work that constantly checks whether the dots truly belong together. Quipu, with its long main filament and side branches, is a good example of this complexity. Its name suggests a cord with knots, but the actual structure is not a neat string. It is a large, uneven, three-dimensional arrangement. Some parts are denser, some are thinner. Some may connect to other features. Some may lie near regions where observation is more difficult. A simple drawing can help us begin, but the real structure is richer than a drawing. It has depth, mass, environment, and uncertainty. That is not a problem. That is what makes it science rather than decoration. The idea of a cosmic superstructure also changes the emotional scale of astronomy. A planet is something we can imagine visiting. A star is something we can imagine orbiting. A galaxy is something we can imagine crossing only with great difficulty, at least in fiction and very optimistic engineering meetings. But a superstructure like Quipu is not really a destination. It is too large for that. You would not travel to Quipu the way you travel to Mars, or even the way a fictional starship travels to another galaxy. You're dealing with a region of the universe, not a stop on a route. Saying you're going to Quipu would be a little like saying you're going to the Northern Hemisphere. It is a place in a broad sense, but not a single address, and yet naming it helps. Names make maps more human. The structure existed long before anyone called it Quipu. It existed before humans, before Earth had complex life, before the Sun was born, depending on which stage of its matter distribution we mean. But the name gives us a handle. It lets us talk about it, compare it, study it, and remember it. Without names, the universe becomes a list of coordinates. With names, it becomes a landscape. Quipu is still a scientific structure, but it is also a landmark in the mind. It is worth being careful here, because a superstructure being named does not mean it is separate from everything around it in a perfectly clean way. The universe does not label its parts with tape. Humans do the labeling because labels help us think. The cosmic web is continuous in many regions. Filaments merge into clusters. Clusters sit inside broader overdensities. Voids press against walls. The boundaries are often chosen using practical definitions. This is not a flaw. It is how we make sense of a universe that changes gradually rather than in neat boxes. So what is a cosmic superstructure really? It is a large coherent feature in the distribution of matter across the universe. It is built from smaller structures, especially galaxy clusters and filaments. It is traced by galaxies, hot gas, X-rays, redshifts, and gravitational effects. It may not be one gravitationally bound object, but it is still a physically meaningful pattern. It is part of the cosmic web, the immense network produced by gravity acting over billions of years on tiny early density differences. Quipu is one of the largest known examples of such a feature, a long, massive arrangement in the nearby universe, named for a knotted cord because that is what its mapped form suggests. Across the largest maps astronomers can make, the universe stops looking like a scatter of isolated galaxies and begins to look like a network. Not a neat network, not a tidy diagram with straight lines and polite labels, but a huge uneven web of crowded regions, long connections, broad sheets, and quiet gaps. This is the cosmic web, and it is the setting that makes Quipu possible. Without the web, Quipu would be just an odd name attached to a large collection of objects. With the web in mind, it becomes part of a much larger story, a story about how gravity slowly gathered matter into a structure so vast that galaxies are not the main characters anymore. They become the bright markers along the threads. It can feel strange at first to think of the universe as a web, because when we look up at the night sky, we do not see it that way. We see points of light. Stars seem scattered above us in darkness. If the sky is clear and dark enough, the Milky Way may appear as a pale band. But even that is only our view from inside one galaxy, looking through its crowded disk. The cosmic web is not something the eye can see from Earth. It is too large, too faint, and too three-dimensional. To notice it, astronomers have to measure where millions of galaxies are, how far away they are, how they cluster, and where the spaces between them open into enormous voids. Only then does the pattern appear. A useful way to picture it is to imagine turning a light on inside a very dark room filled with mist. At first, you might only see the nearest wisps. Then, as the light grows stronger and the room is mapped more carefully, you begin to notice that the mist is not evenly spread. It gathers in strands, it thins in some places, it thickens in others. There are knots where several strands meet. The universe behaves in a somewhat similar way on its larger scales, except the mist is matter, the knots are galaxy clusters, the strands are filaments, and the room is larger than anything a room has any right to be. This web did not appear all at once. In the earliest stages of the universe, matter was spread almost evenly, but not perfectly. That almost is one of the most important words in cosmology. If matter had been perfectly smooth, gravity would not have had much to work with. Every region would have pulled equally in every direction, and structure would have struggled to grow. But the young universe contained tiny differences in density. Some places had just a little more matter than others. Not much, not dramatic. Nothing like a galaxy or a cluster yet. Just small variations, slight unevenness in the cosmic beginning. Over time, gravity amplified them. A region that started with a little more matter had a little more gravity. Because it had more gravity, it attracted more matter. As more matter flowed in, its gravity became stronger, attracting still more. That simple feedback, repeated over billions of years, helped turn small, early differences into the great structures we see today. The universe did not need to plan the web. It did not need a blueprint hidden under a cosmic clipboard. It only needed gravity, time, expansion, and small initial variations. Give gravity enough patience, and it becomes an excellent organizer, though perhaps not the neatest one. Dark matter played a central role in this process. Ordinary matter, the matter that makes stars, planets, gas clouds, people, curtains, biscuits, and the slightly mysterious dust that collects behind furniture, is only part of the matter story. Dark matter does not shine, so telescopes cannot see it directly. It does not glow in visible light, radio waves, or X-rays. But it has gravity, and that gravity shaped the large-scale framework of the universe. In the early universe, dark matter began gathering into a vast invisible network. Ordinary matter then fell into the gravitational wells created by it. Gas collected, galaxies formed, clusters grew. the visible universe lit up along a structure that was already being guided by something unseen. This is why astronomers often describe dark matter as scaffolding. The word is helpful because scaffolding supports a building while not being the finished room you live in. Dark matter provided the gravitational framework. Galaxies and clusters formed along that framework. What we see through telescopes is therefore not the whole web, but the illuminated part of it. The galaxies are like lamps hung along a road at night. They show us where the road is, but they are not the road itself. Quipu, traced by galaxy clusters, is one of the huge illuminated patterns along this deeper dark matter scaffolding. The cosmic web has several main parts. There are knots, where matter is densest. These knots are often occupied by galaxy clusters, the massive gatherings of galaxies, hot gas, and dark matter we have already met. There are filaments, long strands of galaxies and gas stretching between those knots. There are sheets or walls, broader flattened regions where matter spreads across large areas. And there are voids, immense regions with relatively few galaxies. Voids are not completely empty because space is rarely that simple, but they are much emptier than the filaments and clusters around them. Together, these parts form the large-scale pattern of the universe. The word void can sound a little dramatic, as if it belongs in a warning label. Do not enter the void without snacks. But cosmic voids are not sinister holes. They are vast underdense regions, places where gravity has drawn much of the matter away into nearby filaments and clusters. A void can be tens or even hundreds of millions of light years across. If a galaxy sits inside one, it may have fewer neighbours, fewer close interactions, and a very different environment from a galaxy inside a dense cluster. The voids help define the web as much as the crowded regions do. A thread only looks like a thread because there is emptier space around it. This is a useful point to hold on to. The cosmic web is not just about where matter is, it is also about where matter is not. The pattern depends on contrast. Clusters are dense because voids are sparse. Filaments stand out because the regions beside them are thinner. The universe, on these scales, is a landscape of crowded and quiet places. Quipu is one of the crowded patterns, a long arrangement of matter standing out against the less dense regions around it. Galaxies do not simply sit in this web like decorations pinned to fabric. They are shaped by their positions inside it. A galaxy in a dense cluster may experience frequent interactions. It may pass near other galaxies. It may have gas stripped away by hot cluster gas. Its supply of fresh gas may be reduced, changing how it forms stars. A galaxy in a filament may be part of a long flow of matter moving toward denser knots. A galaxy in a void may live more quietly, with fewer close neighbours and a different growth history. The web is not just a map. It is an environment. This is one reason astronomers study large-scale structure so carefully. The web helps explain how galaxies grow and change. It also helps test our understanding of cosmology. If simulations based on dark matter, dark energy, gravity, and early density variations produce a web like the one we observe, that is a good sign. It means the broad model is capturing something real. If the observed universe were arranged in a completely different way, with no filaments, no voids, no clusters or structures far beyond what simulations could create, then cosmologists would have a serious problem and probably several very intense meetings involving coffee. Quipu fits into this web as one enormous feature. It is not separate from the cosmic web, any more than a long mountain range is separate from the geology of a continent. It is an expression of the web. It is a place where clusters and connecting structures line up into a massive extended form. Its name, borrowed from knotted chords, works so well because the cosmic web itself has a chord-like character. There are knots, strands, branches, and connections. Quipu is one of the biggest known arrangements of these cosmic knots and strands. To appreciate this, it helps to step through the scale again, slowly. A star is large. A galaxy is a city of stars. A galaxy group is a small family of galaxies. A galaxy cluster is a major gathering, full of galaxies and hot gas. A filament is a long bridge-like region connecting clusters across huge distances. A superstructure like Quipu is a larger pattern made from clusters and filaments, extending across hundreds of megaparsecs. Each level is built from the one below it, not like bricks stacked neatly, but like traffic patterns growing out of roads, towns, and regions. There is no hard switch where one level ends and the next begins. The universe grows complicated gradually. That gradual complexity is part of why the cosmic web was not obvious for most of human history. Early astronomers mapped stars. Later they realized some faint cloudy patches were other galaxies. Then, as galaxy surveys grew, they found that galaxies were not randomly distributed. They formed clusters. Then clusters formed larger associations. As surveys covered wider areas and measured more distances, the filaments and voids became clear. The web was not discovered in one single moment. It emerged from better maps, the way a picture emerges when enough pieces of a puzzle are placed together. There is a lovely quietness in that. The web was always there, but we had to learn how to see it. Not by looking harder with eyes alone, but by measuring more carefully. A galaxy on a photograph is a point or a smudge. Give it a distance and it becomes a point in three-dimensional space. Give distances to millions of galaxies and the points begin to form a structure. Add clusters, X-ray observations, gravitational lensing and simulations, and the structure becomes deeper. The cosmic web is not just seen, it is reconstructed. Quipu's discovery depends on that reconstruction. If astronomers had only the positions of clusters on the sky, they might see a rough alignment, but not know whether the clusters were truly part of the same structure. Some could be much nearer, others could be much farther. The sky can fool us because it flattens depth. Redshift measurements restore that depth. They allow astronomers to place clusters in a three-dimensional cosmic map. Once that map exists, a long structure like Quipu can be identified as a real feature rather than a chance alignment. There is something almost humble about this. The universe is too large for direct human experience, so we build careful methods to make it understandable. We cannot fly outside the cosmic web and take a photograph from beyond it. We cannot step into a neighbouring universe, lean over the railing and say, "Ah yes, there it is, looking very webby today." We are inside the structure we are mapping. Every observation is made from one small planet in one galaxy. And yet, by measuring light, distance, motion and energy, astronomers can infer the shape of enormous regions around us. That is not a small achievement. It is one of the great quiet triumphs of science. The cosmic web also reminds us that the universe is not static. The web has evolved over time. In the early universe, the pattern was much smoother. As gravity acted, structures grew. Filaments became more pronounced. Clusters became more massive. Voids expanded as matter moved away from them toward denser regions. Even now, galaxies continue moving within this large-scale structure. Clusters continue to grow by accreting matter along filaments. The web is not a frozen decoration. It is a slowly changing architecture. The word slowly is doing a great deal of work here. Human life is short compared with cosmic structure formation. A galaxy cluster does not noticeably rearrange itself over a weekend. A filament does not tighten while you're making tea. But over millions and billions of years, the changes are enormous. Matter flows along filaments into clusters. Galaxies merge. Gas heats. Stars form and die. Voids become more empty by comparison. If we could watch the universe sped up across cosmic time, the web would look alive, not in the biological sense, but in the sense of motion, growth, and constant gravitational adjustment. Filaments are especially important in this picture. They are the highways of the cosmic web. Galaxies and gas can flow along them toward clusters. They connect dense nodes across great distances. In simulations, filaments appear naturally as gravity pulls matter out of expanding underdense regions and channels it into denser lines. Observationally, they can be difficult to detect directly, because the gas inside them may be faint, warm and spread out. But their influence is clear in the distribution of galaxies and clusters. Quipu's long form can be understood as a superstructure dominated by this filamentary character, a huge connected region where the knots and strands of the web become especially prominent. The web also has a relationship with light. As light from distant objects travels across the universe, it passes through regions of different density. Massive structures can bend light through gravitational lensing. Changing gravitational fields can leave subtle imprints on ancient radiation. Dense regions can influence how we interpret large-scale observations. This means that a superstructure is not only something located out there, it can affect what we see beyond it. The universe is not a clean window. It is more like looking through layers of glass, some nearly invisible, each one adding a tiny alteration. For precision cosmology, even tiny alterations matter. That is one reason Quipu is important beyond its record-breaking size. It is part of the nearby cosmic web, and nearby large structures can affect our measurements of the broader universe. If astronomers want to understand cosmic expansion, the cosmic microwave background, or the large-scale flow of galaxies, they need to know where the major nearby concentrations of matter are. A superstructure like Quipu is not just a faraway curiosity. It is part of the foreground landscape through which we study the deeper cosmos. The cosmic web also gives a new feeling to the idea of location. On Earth, we know our addresses through nested places, a room in a house on a street. A street in a city in a country. In space, the nesting continues in a very different way. Earth orbits the Sun. The Sun sits in the Milky Way. The Milky Way belongs to the local group. The local group lies within larger flows and structures in the nearby universe. Beyond that, there are superclusters, filaments, voids, and superstructures. Our address is not only a point, it is a position inside a web. That can be oddly comforting. It means we are not in a universe of lonely islands scattered without connection. The galaxies are related by the history of matter itself. The Milky Way is not isolated in some absolute sense. It is part of a larger environment, shaped by gravity, dark matter, and cosmic expansion. Even if the distances are too great for travel, the relationships are real. The universe has neighborhoods, roads, dense cities, quiet regions, and long connecting routes. Of course, all of these comparisons are only tools. The cosmic web is not actually a spider's web. It was not woven by an animal. It is not sticky, though gravity can be persuasive in its own way. It does not hang in space as a flat pattern. It is three-dimensional, evolving, uneven, and built from matter responding to gravity over time. The web metaphor works because it helps us picture connections and gaps. But the real structure is more complex than any household web in a corner, however impressive the spider may be. A better mental image might be a vast foam, where matter gathers along the surfaces and edges of expanding bubbles, leaving emptier spaces inside. Or a sponge with material forming walls around holes, or a network of rivers where smaller streams feed larger channels. Each image helps with one part and fails at another. The web image is still the most widely used because it captures the strands and knots so well. For Quipu, it is especially fitting, because a Quipu itself is made of cords and knots. The cosmic web gave us the pattern. The ancient cord gave us the name. As you picture it now, imagine moving farther and farther away from the Milky Way. At first, our galaxy fills the view, a wide spiral with star-forming arms and a bright centre. Then nearby galaxies appear, Andromeda, Triangulum, and many smaller companions. Pull back farther, and groups and clusters begin to matter. Pull back again, and individual galaxies become like tiny sparks. The sparks are not evenly scattered. They gather along threads. The threads meet in bright knots. Between them, huge dark spaces open. Continue pulling back, and one of those enormous arrangements begins to resemble a long cord with side branches. That is where Quipu enters the map. The remarkable thing is that all of this structure grew from conditions in the early universe. The cosmic microwave background, the leftover light from when the universe became transparent, shows tiny temperature variations. Those variations are connected to the density variations that later grew into structure. In other words, the seeds of the cosmic web were present when the universe was very young. Quipu's matter distribution today is part of a chain of cause and effect stretching back more than 13 billion years. A tiny unevenness in the beginning, amplified by gravity, shaped by dark matter, slowed and stretched by expansion, eventually becomes galaxy clusters, arranged across a billion light-year scale. That is not abstract when you break it down. More matter in one place pulls in more matter. Less matter in another place loses matter to its surroundings. Gas follows gravity. Galaxies form where gas becomes dense enough. Clusters grow where many galaxies and dark matter halos gather. Voids open where fewer structures form. Filaments remain as the channels between dense regions. The web is the result of many concrete physical processes acting together step by step across enormous time. And Quipu is one of the largest visible consequences of that process. It is not floating outside the story. It is the story made large enough to notice. It shows how far the web can stretch, how massive its knots can become, and how connected the nearby universe really is. It helps us see that galaxies are not merely scattered lights. They are part of a grand arrangement, one that can be mapped, measured, simulated, and named. If the web can make structures like this, why did Quipu grow to such an enormous size? What conditions allowed one pattern of clusters and filaments to stretch so far across the nearby cosmos, becoming not just another strand in the web, but one of the largest structures ever recognized within it? The answer begins with a simple idea that turns out to be very powerful. Quipu is enormous because the universe had enough time, enough gravity, enough dark matter, and enough unevenness at the beginning for matter to gather into a vast connected pattern. It did not grow like a tree from one seed. It did not expand outward from a single central point like a balloon being filled. It formed as part of the cosmic web, where many dense regions slowly became connected by filaments, and where galaxy clusters mark the heaviest knots in a much larger arrangement. So when we ask why Quipu is so large, we are really asking why the universe is able to build structures on scales that make even galaxies look like small details on a much bigger map. That can be a difficult thought to hold at first, because our everyday experience of size is built from familiar things. A hill is large if you have to walk up it. A building is large if you have to tilt your head back to see the top. A country is large if travelling across it requires planning, snacks, and at least one moment where someone says, "Are we nearly there yet?" But Quipu belongs to a different category of size. It is not large because it is packed tightly into one place. It is large because the pattern extends across an enormous region of space. Its length is measured in hundreds of megaparsecs, which means more than 1 billion light-years from end to end. It is a structure made not from one solid body, but from many galaxy clusters and connecting regions arranged across a vast stretch of the nearby universe. The first reason Quipu could become so large is that the early universe was not perfectly smooth. This may sound like a small detail, but it is one of the most important facts in cosmology. Shortly after the Big Bang, matter and radiation were spread almost evenly, but not exactly evenly. Some regions were a little denser than others. The differences were tiny, far too small to look like galaxies or clusters at the time, but gravity notices small differences. Gravity is patient in a way that very few things on Earth are. It does not get bored. It does not decide to check its phone. It simply keeps pulling. If one region has slightly more matter than its surroundings, it has slightly stronger gravity. That extra gravity pulls in more matter. More matter makes the region denser. A denser region pulls harder. Over billions of years, that quiet feedback can turn a tiny early wrinkle into a galaxy cluster, a filament, or a superstructure. This is where dark matter becomes essential. Ordinary matter, the kind that forms stars, planets, gas clouds, and sleepy people under blankets, is only part of the matter in the universe. Dark matter does not shine or reflect light, but it has gravity. Because it interacts mostly through gravity, it could begin forming the broad scaffolding of cosmic structure early on. Ordinary matter fell into that gravitational framework later, collecting into galaxies and clusters where dark matter had already helped deepen the wells. If ordinary matter is the visible furniture of the universe, then dark matter is much of the hidden framing inside the walls. You may not see it directly, but the shape of everything depends on it. Quipu is enormous because it is part of that dark matter framework. The galaxy clusters used to trace it are not random bright decorations. They are massive places where matter has gathered strongly, and each one marks a deep gravitational concentration. When many of these concentrations lie along a connected arrangement, they reveal a larger structure. The visible galaxies and hot gas are the signs we can detect. The full mass includes much more, especially dark matter. This is why Quipu's estimated mass is so huge. The stars alone are not the whole story. The galaxies are not the whole story. Even the hot gas is not the whole story. A large share of the structure's mass is invisible, known through gravity and through the way matter arranges itself. Another reason Quipu is so large is that the universe builds structure in a web-like way, rather than in isolated round piles. If gravity simply pulled matter into separate balls, the large-scale universe would look very different. Instead, cosmic expansion and gravitational collapse work together to create sheets, filaments, knots, and voids. Matter drains away from underdense regions and collects along boundaries between them. Imagine a surface with many shallow dips and raised seams, except stretched into 3 dimensions and filled with galaxies rather than crumbs from a late-night snack. Matter tends to gather along the seams. The densest places become clusters. The long seams become filaments. Several filaments can meet and form larger superstructures. Quipu's size comes from being connected through this filamentary arrangement. It is not one cluster that somehow became impossibly huge. It is a chain-like pattern of clusters and branches, a long extended region of higher density. That makes its size easier to understand. A single city can be large, but a road network connecting many cities can be much larger. Quipu is more like that road network. The galaxy clusters are the big cities. The filaments are the routes between them. The whole superstructure is the large regional system that appears when you map those cities and routes together. It is still physically meaningful, but it is not one compact object. This helps prevent a common misunderstanding. When people hear that Quipu is the largest structure ever found, it is tempting to picture a single enormous object floating in space, perhaps like a cosmic wall or a giant glowing rope. But Quipu is not solid. It is not something you could fly around and see from the outside like a planet. It is a large-scale pattern in the distribution of matter. Its size is defined by how far that connected pattern extends. This does not make it less real. A river system is real even though it includes many streams, branches, banks, and changing edges. A mountain range is real even though it is made from many peaks and valleys. Quipu is real in that same broad physical sense. It is a coherent feature of the cosmic landscape. The expansion of the universe also plays a role in the story. On small scales, gravity can overcome expansion. The Earth does not expand away from the Moon. The solar system does not expand apart. The Milky Way is held together by gravity. Galaxy clusters are held together as large gravitational systems. But on the larger scales, the expansion of the universe matters. A superstructure as enormous as Quipu does not have to be gravitationally bound as one single object in the way a cluster is. Parts of it can be connected as a pattern in the matter distribution, without all of it being destined to collapse into one future object. This is important because it explains how something can be so long without needing to behave like one giant galaxy cluster. In other words, Quipu is large partly because the word structure is being used carefully. It refers to a connected overdensity across a great distance, not to a single hard-edged object. The universe can contain patterns larger than its bound objects. A weather system on Earth can stretch across a continent, but that does not mean it is a solid thing you can put in a box. It is a real system, with pressure, motion, temperature and effects, but its edges are soft. Quipu is more stable and much grander than a weather system, of course, but the comparison helps. It is a real arrangement with measurable mass and structure, even though it is not a single compact body. The next piece is time. Quipu is enormous because the universe is old. Structure formation is slow. Galaxy clusters do not appear overnight. Filaments do not assemble in a hurry. The universe has had more than 13 billion years for gravity to amplify those early density differences. During that time, matter flowed into denser regions, galaxies formed, clusters grew, and filaments became more pronounced. When we look at Quipu, we are seeing the result of an extremely long process. It is not an instant creation. It is an accumulated outcome. This slow growth is easier to picture if you think of a landscape forming under the influence of water. A single rainstorm can make small streams. Many seasons of water flow can carve channels. Many more can shape valleys. The cosmic web is not carved by water but by gravity acting on matter across time. The early universe supplied the uneven starting pattern. Dark matter provided the main gravitational skeleton. Ordinary matter lit up parts of that skeleton with stars and hot gas. Over billions of years, the web became more defined. Quipu is one of the places where that definition became especially large and clear. It is also large because it sits in a region where many dense structures happen to be part of the same broader arrangement. Cosmic structures are not evenly sized. Some filaments are short, some are long, some clusters are isolated compared with others. Some regions of the universe have many clusters linked through denser environments. Quipu appears to be one of those exceptional alignments of matter, where the local cosmic geography produced a very long superstructure. This does not mean it was designed or aimed. It means the natural processes of structure formation created a particularly prominent feature in this part of the nearby universe. There is a useful balance here. Quipu is extraordinary, but it is not necessarily a violation of what cosmologists expect. The researchers compared structures like Quipu with simulations based on the standard cosmological model, and similar superstructures can appear in those simulations. That matters. It means that the same physics used to explain the cosmic web in general can also produce rare, very large features. Quipu may be a record holder, but a record holder can still belong to the rules of the game. The tallest tree in a forest is unusual, but it is still a tree. It tells you something about what the forest can produce under the right conditions. This is a less flashy conclusion than saying Quipu breaks the universe, but it is also more satisfying. The universe does not need to be broken to be surprising. It can be lawful and still astonishing. Gravity, dark matter, expansion, and time can work together to make something so large that our normal sense of scale gives up and asks politely for a chair. That is one of the best parts of astronomy. It shows that the ordinary rules, when allowed to operate across extraordinary scales, can lead to results that feel almost impossible. Quipu's size is also connected to how astronomers identify superstructures. When researchers map galaxy clusters and define which ones are linked, the chosen criteria affect the structure's measured length and membership. If the linking scale is too small, a huge feature may be split into separate pieces. If it is too large, unrelated regions may be joined together too loosely. The goal is to choose a method that identifies meaningful overdensities without exaggerating them. For Quipu, the structure stood out as the largest among the prominent superstructures in the studied volume. Its length reflects the connected arrangement found by the analysis, using galaxy clusters as the tracers. That means the measured size is partly a statement about the universe, and partly a statement about the method used to map it. This is not a weakness. It is how large-scale structure science works. A coastline can have different measured lengths depending on how finely you trace every curve, but that does not mean the coastline is imaginary. A city's boundary can be defined administratively, economically, or by continuous buildings, but the city still exists. Quipu's exact edges may depend on the mapping method, but the large overdense pattern is real enough to matter. Another reason Quipu feels so enormous is that it is being compared with the things we usually use as cosmic landmarks. The Milky Way is about 100,000 light-years across. That is already a distance beyond ordinary imagination. Quipu is more than 1 billion light-years long. This means it is more than 10,000 times the width of our galaxy. A galaxy cluster may span several million light-years. Quipu stretches across hundreds of millions more. It makes the usual cosmic stepping stones feel small. Not unimportant, just small in the way a single street is small compared with a continent-wide transport network. Yet the structure is not dense everywhere along that length. This is another key point. If Quipu were packed uniformly with stars from end to end, it would be something very different. Instead, much of it is empty space, or at least space that is far less dense than the clusters themselves. The mass is concentrated in knots and connections. The huge length comes from the arrangement of those knots over great distances. That is why Quipu can be both incredibly massive and incredibly diffuse. The universe does not need to fill every meter of a structure with matter for the structure to be real. The relationship between the parts is what defines it. Think of a constellation for a moment, but only as a rough comparison. A constellation is a pattern we draw between stars from our viewpoint, and the stars may not be physically close together. Quipu is not like that in the same way, because it is identified in three-dimensional space and traced by real clustering. Still, the comparison helps show why pattern matters. When astronomers identify Quipu, they are not just drawing lines on a flat sky. They are using distances and densities to determine that the clusters form a real large-scale arrangement. It is a physical structure, not an imagined picture. But like many patterns, it becomes visible only when the scale is right. There may also be more to its full extent than we currently know. The Milky Way blocks part of our view of the distant universe along its dusty plane. This obscured region can hide clusters and galaxies behind foreground stars and dust. If Quipu reaches into or beyond such difficult areas, its full connection to surrounding structures may be harder to measure. This does not erase the known structure, but it reminds us that cosmic maps are incomplete in places. Sometimes the largest things are not fully visible at once. Our own galaxy can stand in the way, which is a little rude considering we live here. Quipu's size also matters because of where it is found. It lies in the relatively nearby universe, in the distance range studied by the survey. Nearby, again, means hundreds of millions of light-years, because astronomy uses words with a confidence that can be alarming. But compared with the observable universe as a whole, this region is local enough for large structures to influence certain measurements and observations. A huge nearby superstructure can contribute to local motions, gravitational effects, and subtle changes in how we observe background radiation. So its size is not just a number for a cosmic record book, it has practical consequences for precision cosmology. If astronomers are trying to measure the expansion of the universe, or understand the cosmic microwave background, or trace how galaxies move relative to one another, they need to know about major nearby mass concentrations. A superstructure with Quipu's mass and size is part of the foreground landscape. It is like trying to measure the flatness of a distant horizon while standing near a mountain range. The mountain range affects the view. Quipu does not dominate the whole universe, but it is too large and massive to ignore when mapping the local cosmic environment. There is also the matter of probability. In a universe as large as ours, rare things happen somewhere. This is not a trick, it is just scale. If you roll one die, getting a 6 is ordinary. If you roll 1 billion dice, some unusual patterns will appear. The universe contains an enormous number of regions, galaxies, clusters, and structures. Even if extremely large superstructures are rare, the observable universe gives gravity a vast stage on which to produce them. Quipu may be rare in the nearby universe, but rarity is not the same as impossibility. It is the kind of structure that can emerge when many conditions line up naturally. That said, cosmologists still care very much about how rare it is. If too many structures like Quipu were found, or if one were far larger than simulations predicted, that could become a challenge. Science pays attention not only to what exists, but to how often it should exist. A single large structure may be acceptable within current models. A whole population of unexpected giants might force new thinking. This is why discoveries like Quipu are not just satisfying images, they become tests. They help researchers compare the real universe with simulated universes built from the best current physics. In those simulations, matter evolves under gravity from early conditions similar to what we infer from the cosmic microwave background. Dark matter collapses into halos, gas follows, galaxies form, clusters grow, filaments connect them. Over time, large-scale patterns emerge. When simulations produce superstructures similar to Quipu, it suggests that our basic picture is able to create this kind of giant feature. The details still matter, and the observations still need refinement, but the existence of Quipu fits into the broader story of structure formation. So why is Quipu so enormously large? Because the universe began with tiny unevenness. Because dark matter provided a vast gravitational scaffold. Because gravity amplified small differences over billions of years. Because matter naturally arranged itself into a web of knots, filaments, walls, and voids. Because clusters formed at the densest points and connected along extended structures. Because the expansion of the universe allows very large patterns to exist without requiring them to be single, compact-bound objects. Because in a universe, this old and this wide, rare, large structures are allowed to appear. Quipu is the result of all of those facts working together. It is helpful to imagine Quipu not as a giant object that grew by swelling, but as a giant pattern that emerged by connection. The clusters did not all start in one place and spread outward. They formed within a broader web where matter was already arranged unevenly. Over time, the densest regions became more pronounced, and the connections between them became traceable. Quipu is large because the pattern continues for an enormous distance before fading into the surrounding cosmic landscape. It is the continuity of the arrangement that makes it remarkable. This also gives Quipu a very different feeling from familiar astronomical objects. A star shines because of nuclear fusion in its core. A planet has a surface, an orbit, and a physical body. A galaxy has stars orbiting within a shared gravitational system. A galaxy cluster has a deep potential well holding galaxies and hot gas. Quipu is a higher level feature. It exists because many clusters and surrounding matter trace a larger pattern. It is a structure of structures. That phrase may sound a bit like something written on a whiteboard during a very long meeting, but it is accurate. Quipu is not one building, it is a region of the cosmic city map. And perhaps that is the most important idea to keep as we move forward. Quipu's size is not a mystery in the sense of having no explanation. It is a mystery in the gentler sense of being difficult to fully picture. We can explain the processes that made it possible. We can measure its clusters, estimate its mass, compare it with simulations, and place it in the cosmic web. But imagining the full length of it remains hard because human scale is small. We think in steps, rooms, streets, and years. Quipu asks us to think in galaxy clusters, dark matter scaffolds, megaparsecs, and billions of light years. That difficulty is not something to fight. It is part of the experience. The mind can rest against a scale it cannot completely grasp. You do not need to picture every cluster in Quipu at once. It is enough to understand the basic shape of the idea: a long region of enhanced matter, massive clusters acting as knots, filaments connecting them, dark matter holding much of the unseen framework, gravity building slowly from early unevenness, a structure large not because it is solid, but because the web itself stretches so far. A new question emerges: what exactly lies within this vast structure? Inside Quipu, the word inside needs to be handled gently, because we are not talking about the inside of a box, or the inside of a planet, or even the inside of a galaxy where stars orbit through a shared disk and halo. Quipu does not have a wall. It does not have a ceiling. It does not have a tidy outer skin where you could tap on the edge and say, well, here it begins. A cosmic superstructure is much looser and much larger than that. To look inside, Quipu means to look at the pattern of matter that makes it recognizable, the dense knots where galaxy clusters sit, the long filaments that connect those knots, and the emptier regions around and between them that make the whole structure stand out from the cosmic background. That is a useful place to begin, because the interior of a cosmic web structure is not packed solid. It is not full in the way a stone is full. It is not even full in the way a cloud is full, and clouds are already quite relaxed about boundaries. Quipu is mostly space, enormous amounts of space. If you could somehow travel through it, which would require a vehicle, a lifespan, and a snack cupboard, all beyond present engineering, you would spend almost all your time crossing darkness. The galaxies would still be separated by huge distances. The clusters would be separated by even larger distances. The filaments would not look like glowing ropes from up close. You would not see a bright cord stretching past your window. The structure becomes visible only when you step back through data and map the positions of clusters and galaxies across hundreds of millions of light years. So the first thing inside Quipu is emptiness, but not meaningless emptiness. Space itself is part of the structure. The gaps between clusters matter because they show how the matter is arranged. A city is not only its buildings, it is also streets, parks, empty lots, distances, and routes. A forest is not only its trees, it is also clearings, paths, and the spaces between trunks. In the same way, Quipu is not only its galaxy clusters, it is also the lower density stretches between them, the regions where matter thins, the surrounding voids that help shape the web, and the long corridors where galaxies and gas trace the pull of gravity. The densest pieces of Quipu are galaxy clusters. These are the knots in the cord. Each cluster contains many galaxies, along with hot gas and a large amount of dark matter. The galaxies are the parts we can most easily imagine, because they shine. A spiral galaxy with its arms, an elliptical galaxy with its smooth glow, a small irregular galaxy still forming stars in patches, all of these may be members of clusters, but in a cluster, the galaxies are only part of the total mass. Between them lies extremely hot gas, thin by ordinary standards but spread across such enormous volumes that it adds up to a major component. Around and through all of it is dark matter, the invisible mass that holds much of the cluster together through gravity. The hot gas is especially useful because it shines in X-rays. That is why the clusters in Quipu could be traced so effectively through X-ray surveys. When astronomers find X-ray bright galaxy clusters, they are not simply finding pretty lights. They are finding heavy knots in the cosmic web. The X-ray glow tells them there is hot gas trapped in a deep gravitational well. The gravitational well tells them there is a large concentration of matter. The matter concentration tells them this is one of the places where the web is dense. And when many of these dense places are mapped together, the larger structure begins to appear. A single galaxy cluster is already a vast environment. It may contain hundreds or thousands of galaxies moving through a shared gravitational field. Some galaxies near the center may have had many encounters. Some may have lost gas. Some may have stopped forming stars as actively as they once did. The cluster's hot gas can strip material from galaxies moving through it. a process that sounds rather dramatic because it is. Imagine walking into a strong wind and having your coat pulled backward, except the coat is a galaxy's gas supply, and the wind is a sea of plasma millions of degrees hot. The universe is calm at a distance, but it is not always gentle up close. In Quipu, these clusters are not isolated in the map. They sit along a long main structure with smaller side branches, which is why the comparison to a knotted cord works so well. The clusters are like knots tied along a string, though the string itself is made from the broader distribution of galaxies, gas and dark matter. Some knots are heavier than others, some regions are more crowded, some sections are thinner. The whole shape is uneven, because cosmic structure grows through gravity, not through anyone measuring carefully with a ruler and saying, "Let us keep this symmetrical." Gravity is effective, but it is not especially interested in interior design. Between the clusters lie filaments. These are the long connecting regions of the cosmic web. A filament may contain galaxies, smaller groups, gas and dark matter stretched across enormous distances. Filaments are not solid bridges. They are regions where matter is denser than the surrounding voids, but usually less dense than the clusters at their ends or intersections. If clusters are cities, filaments are the roads and river valleys between them. They guide matter, they connect dense regions, they help explain why galaxy clusters are not just scattered randomly, but arranged into larger patterns. This is one of the most important ideas in understanding Quipu's interior. The structure is not simply a pile of clusters, it is a networked environment. The filaments give the clusters context. Without the filaments, the clusters would be more like separate islands. With filaments, they become part of a connected system. Matter can flow along these filaments over cosmic time. Galaxies and gas can move toward denser regions. Smaller groups can fall into clusters. The clusters grow partly by drawing material from their surroundings. In that sense, filaments are not only lines on a map. They are channels in the history of structure formation. The filaments inside and around Quipu are also part of the dark matter story. Dark matter provides much of the gravitational framework. Ordinary matter gathers where dark matter has already made the gravitational path easier. The galaxies show us some of that path. The hot gas in clusters shows us the deepest parts. But the full filament includes matter we do not see directly. That is why maps of galaxy positions, X-ray clusters and simulations are all needed. Each gives a different view of the same underlying structure. One traces luminous galaxies, one traces hot cluster gas, one traces what gravity should build when dark matter and ordinary matter evolve together. This is also why Quipu is not evenly bright. A filament may contain many galaxies, but spread across so much space that it would look almost empty from a close viewpoint. The human eye is not built to see density across hundreds of megaparsecs. We see nearby contrast. We see lamps, walls, faces, pages, the little red standby light on a television that somehow becomes the brightest object in the universe when you're trying to sleep. Cosmic filaments require a different kind of seeing. They become visible statistically through the measured positions of galaxies and clusters. The pattern is real, but it is too large and too sparse for ordinary sight. Then there are the voids. These are the quieter regions of the cosmic web, the places with fewer galaxies and less matter than average. Voids are not necessarily perfect empty bubbles. They can contain galaxies, faint filaments, gas and dark matter, but compared with the crowded walls and filaments around them, they are underdense. In the architecture of the cosmic web, voids are essential. They are not just missing matter, they help shape where the matter goes. As the universe evolves, matter tends to drain away from underdense regions and collect along denser boundaries. The voids expand in a relative sense, while filaments and clusters become more defined. Around a superstructure like Quipu, voids act almost like the open spaces around a mountain range or the sea around a chain of islands. They help reveal the shape. A dense structure only stands out because the surrounding regions are less dense. The long chord of Quipu can be identified because the clusters, and galaxies along it are more concentrated than the regions around it. Without contrast, there would be no visible structure. If matter were spread perfectly evenly, there would be no Quipu, no filaments, no clusters, no cosmic web, and astronomy would be much tidier but far less interesting. The word void can make these regions sound useless, but that would be unfair. Voids are laboratories for understanding the universe. Galaxies in voids may evolve differently from galaxies in dense regions. They may have fewer interactions and a quieter supply of material. Voids also help cosmologists test models of structure formation because their sizes, shapes, and distribution depend on how matter evolved under gravity. In the case of Quipu, the voids and lower density regions nearby are part of what define the superstructure's boundaries. The structure is not just where the clusters are, it is also where the clusters are not. Inside a mapped superstructure, there can be lower density gaps between major knots and filaments. That may seem odd at first. How can an enormous overdensity contain emptier regions? But this happens at many scales. A city can have parks, a forest can have clearings, a galaxy can have spaces between stars so large that a starship, if we had one, would almost never come close to anything. Quipu is a large-scale overdensity compared with the wider cosmic average, but that does not mean every part of it is crowded. Its interior is textured. Dense knots, thinner filaments, branching extensions and quieter gaps all belong to the structure. This texture is one reason Quipu's shape is so important. A simple round concentration would tell one kind of story. A long filament with side branches tells another. It suggests matter arranged along the web, with clusters marking the denser nodes and side filaments showing where additional connections extend from the main spine. The shape is not decorative. It is evidence of how the structure formed. The universe tends to build large-scale features through anisotropic collapse, which simply means matter does not fall together equally from all directions. It collapses first into sheets, then filaments, then knots, producing a web-like pattern rather than a set of neat spheres. Quipu's long, spine-like form fits this broader pattern. It is one of the places where the web becomes unusually large and clear. The main filament contains many cluster knots, and the side filaments make the whole thing resemble a cord with hanging threads. That image is not just a nice name choice, it helps describe the geometry. A Quipu used knots along cords to record information. Cosmic Quipu is a record written in matter, with clusters acting as knots along a gravitational cord. The difference is that the ancient version could be held in human hands, while the cosmic version is longer than 1 billion light-years, which makes storage slightly more complicated. The clusters inside Quipu also sit in environments richer than isolated clusters. In the study, galaxies around superstructures remain overdense, over larger distances from member clusters than galaxies around clusters outside superstructures. That means a cluster inside a superstructure is not just a cluster with a few neighbours nearby. It belongs to a broader, dense environment. The surrounding galaxy density stays elevated farther out. This is important because it shows that superstructures are not just artificial chains drawn between clusters. They are special environments where the wider matter distribution differs from the field. A field cluster, meaning one not associated with a major superstructure, may still be massive and interesting. It may still contain many galaxies and hot gas, but its surroundings can be less rich on large scales. In a superstructure, the cluster is embedded in a broader overdensity. The neighbourhood itself is different. This can matter for galaxy evolution. A galaxy entering a cluster through a filament may already have been shaped by group environments before it arrives. Astronomers sometimes call this pre-processing. Before a galaxy reaches the dense centre of a cluster, it may have interacted with other galaxies in a group, lost some gas, or changed its star formation. The cosmic web does not wait until the final destination to begin shaping galaxies. The journey matters. That makes Quipu an enormous environmental system. It is not only a large structure to measure, it is a setting where galaxy clusters Groups and filaments may influence the galaxies within them across huge distances. A galaxy in one of Quipu's filaments may not experience the same life as a galaxy drifting in a sparse void. A galaxy near one of its cluster knots may face strong gravitational interactions and hot gas effects. A galaxy in a side filament may be part of a slow flow toward a denser region. All of these environments are connected by the larger web. There is a quiet complication here, because astronomers cannot simply label every galaxy in the region with perfect certainty. Surveys have limits. Some galaxies are too faint. Some regions are obscured by the Milky Way. Distances have uncertainties. The zone of avoidance, where our own galaxy blocks part of the view, affects the mapping of Quipu near some directions. Quipu may extend toward hidden structures, and nearby features like the Vela region complicate the picture. This does not erase what is known, but it reminds us that the map is still improving. Cosmic geography is a work in progress. The zone of avoidance is especially inconvenient because it hides exactly the kind of information astronomers want when tracing very large structures. Dust and stars in the Milky Way interfere with our view of distant galaxies and clusters. In the case of Quipu, parts of the structure reach toward obscured regions, and the question of how it connects to nearby hidden structures remains important. It is a little like trying to map a huge river system when a thick fog covers one bend in the river. You can see enough to know the river is real, but you still want to know exactly what happens inside the fog. Even with that difficulty, the broad internal picture is clear enough to be meaningful. Quipu contains major cluster concentrations, long filamentary connections, side branches, and surrounding lower density regions. It is a structure of contrasts. Dense knots stand against thinner strands. Filaments stand against voids. The whole superstructure stands against the average density of the nearby universe. Its great size does not come from uniform fullness, but from extended organization. This is a useful thought for the sleepy mind, because it turns an overwhelming number into a landscape. Quipu is not only 428 megaparsecs, it is a chain of cluster cities. It is a set of long matter roads. It is bordered and shaped by quieter cosmic regions. It contains bright galaxies, hot gas, invisible dark matter, and huge stretches where very little happens by human standards. It is not a single object, but a connected environment. And that environment has enough structure to be recognized from our distant data-built viewpoint. If you imagine moving along Quipu from one end to the other, not quickly, because nothing about this journey could be quick, the scenery would change slowly and drastically at the same time. For millions of light years, you might travel through sparse regions where galaxies are few and far apart. Then a filament would become richer. Groups of galaxies would appear more often. The gravitational pull toward a dense knot would grow. A cluster would come into view, not as one neat object, but as a vast swarm of galaxies embedded in hot X-ray gas and dark matter. Past that cluster, the density might thin again, then gather along another strand, then branch toward a side filament. The structure would not feel like a tunnel. It would feel like moving through a cosmic landscape of changing density. Of course, no human could actually make such a journey. Even light needs more than 1 billion years to cross Quipu's full length. But the mental journey helps. It allows the structure to become more than a statistic. It becomes a place in the large-scale universe, with dense regions and quiet regions, with main routes and branches, with clusters that act as landmarks and voids that act as open spaces. The more clearly we imagine those parts, the less Quipu feels like a single impossible giant, and the more it feels like a natural result of the cosmic web. This is also why the study of Quipu connects to so many different areas of astronomy. Galaxy cluster physics appears in the hot gas and dark matter knots. Galaxy evolution appears in the environments around clusters and filaments. Cosmology appears in the structure's mass, size, and comparison with simulations. Observational astronomy appears in the X-ray surveys and galaxy redshift maps. even the limitations of our viewpoint appear in the zone of avoidance. Quipu is not just one discovery. It is a meeting place for many kinds of evidence. The clusters, filaments, and voids inside and around Quipu tell us that the universe is not arranged like a simple set of objects floating in emptiness. It is arranged through relationships. Dense regions pull, sparse regions empty out. Matter flows along preferred directions. Galaxies grow differently depending on where they live. Clusters mark the deepest knots. Filaments connect them. Voids shape the gaps. And from far enough away, these pieces form a pattern large enough to earn a name. By this point in the journey, Quipu is no longer just a huge name attached to a huge distance. It has become a landscape, a long arrangement of galaxy clusters, filaments, side branches, and surrounding emptier regions, all traced through careful maps of the nearby universe. But once a structure becomes this large and this massive, it does not simply sit quietly in the background like a decoration on the cosmic wall. It begins to matter for the way we measure the universe itself. Not because Quipu is doing anything dramatic or dangerous, and certainly not because it is reaching toward us with a billion light-year-long hand, which would be impolite, but because mass changes how light travels, how galaxies move, and how astronomers interpret what they see. This is the important shift. Quipu is not only something we look at, it is also something we may have to look through, around, and mathematically account for. A nearby superstructure with an estimated mass of hundreds of quadrillions of suns is part of the foreground scenery of the universe. It lies between us and some of the deeper cosmic background we try to study. It contributes to the local pattern of gravity. It helps shape the movement of galaxies in its neighbourhood. It can leave subtle marks on ancient light that has crossed the universe. In simple terms, Quipu can warp our view, not in the science fiction sense of bending space into a tunnel for a starship, but in the observational sense of making the universe look slightly different than it would if Quipu were not there. The first way to think about this is through gravity. Every concentration of mass has gravity. A planet has gravity. A star has gravity. A galaxy has gravity. A galaxy cluster has a great deal of gravity. A superstructure like Quipu is more diffuse than a cluster, but it contains so much mass spread across such a large region that its gravitational influence matters on very large scales. Gravity does not need a solid surface to work. It does not ask whether a structure has neat edges or a visitor centre. If mass is there, space-time responds. Light passing through or near that mass can be slightly deflected. Galaxies nearby can have their motions affected. Background signals can be altered in small but measurable ways. A helpful comparison is looking through a window with slightly uneven glass. If the glass is very warped, the world outside looks obviously distorted. Straight lines bend, shapes stretch, faces become briefly alarming. But if the glass is only slightly uneven, the distortion may be subtle. You might not notice it at first. Still, if you're trying to measure the exact position of something far away, that tiny distortion matters. The universe has its own version of uneven glass, created by gravity. Massive structures bend the paths of light. This is gravitational lensing, and it is one of the most useful and beautiful effects in astronomy. Gravitational lensing can be strong or weak. Strong lensing happens when a massive object, often a galaxy cluster, bends light so dramatically that it creates arcs, rings, or multiple images of a background galaxy. Those images can look like someone has gently smeared a galaxy around the edge of invisible gravity. Weak lensing is much subtler. It slightly changes the shapes and orientations of many background galaxies. No single galaxy image may scream, "I have been lensed, please file a report." But when astronomers measure many background galaxies statistically, the pattern reveals the mass in the foreground. This is one way scientists map dark matter. A structure as large as Quipu can contribute to this kind of large-scale lensing environment. It is not a single compact lens like one massive cluster at its centre. Instead, its influence is spread out across clusters, filaments, and surrounding matter. The effect is faint and broad. It may slightly distort the images of more distant objects across a large region of sky. For casual stargazing, this is not something you would notice. For precision cosmology, where tiny differences matter, it becomes part of the accounting. If you want to understand the universe accurately, you must know what massive structures are in the foreground, because the foreground is not empty. This matters especially because modern cosmology often depends on very small effects. Astronomers are not only counting bright objects, they are measuring subtle patterns in galaxy shapes, tiny temperature variations in the cosmic microwave background, small deviations in galaxy motions, and delicate traces of cosmic expansion. It is a little like trying to hear a soft note in a large quiet room, while someone across the room is slowly moving furniture. The furniture is not necessarily loud, but if you care about the soft note, you need to know what else is happening in the room. Quipu's effect on the cosmic microwave background is one of the most interesting parts of the story. The cosmic microwave background, often shortened to CMB, is the oldest light we can observe directly. It comes from a time when the universe was about 380,000 years old, when space had cooled enough for light to travel freely. Today, that ancient light reaches us as a faint microwave glow from every direction. It is almost uniform, but not perfectly. Tiny variations in its temperature help tell us about the early universe, its matter content, its expansion, and the seeds of structure that later became galaxies and clusters. Because the CMB is so old and comes from so far away, it has travelled through the universe for billions of years before reaching our instruments. Along the way, it passes through the gravitational fields of cosmic structures. If those gravitational fields were completely static, a photon falling into a gravitational well would gain energy, then lose the same amount of energy climbing out, ending up as it began. But the universe is expanding, and dark energy affects the growth and evolution of large-scale structures. The gravitational wells associated with structures can change while the photon is passing through them. This can leave a small temperature shift in the CMB. That effect is called the integrated Sachs-Wolf effect. The name sounds formal, and it is. Integrated Sachs-Wolf has the energy of a phrase that entered the room wearing a very serious jacket. But the basic idea can be made friendly. Imagine a ball rolling into a dip and then rolling out the other side. If the dip stays exactly the same, the ball gains speed going down and loses speed going up, and the two effects cancel. But if the dip becomes shallower while the ball is crossing it, the ball does not lose quite as much energy climbing out as it gained falling in. Something similar can happen to CMB photons moving through evolving gravitational potentials. They can gain or lose tiny amounts of energy depending on the changing structure they pass through. A huge nearby superstructure like Quipu is the sort of thing that can contribute to this effect. The researchers who studied these nearby superstructures found that they should produce a modification in the CMB through the integrated Sachs-Wolf effect. They searched for a signal in Planck satellite data and found one with the expected strength, though with low statistical significance. That last part matters. It means the signal is not strong enough yet to treat as a clean, decisive detection from Quipu or the related superstructures alone. The universe is noisy in the statistical sense, and the CMB already contains many tiny variations from many causes. Picking out one faint foreground imprint is difficult. It is like trying to identify the exact ripple from one small stone after many stones have been tossed into a pond. Still, the possibility is important. Quipu may not blaze across the CMB like a bright scar. It may leave only a subtle temperature pattern, a small change buried among other signals. But small does not mean unimportant. Many of the most powerful measurements in cosmology are small. A tiny shift can test a model. A faint correlation can reveal a hidden structure. A weak signal, measured carefully enough, can confirm that our understanding of gravity, expansion, and matter distribution is on the right track. Quipu is not shouting at the cosmic microwave background, it is whispering into it. Astronomers are trying to hear whether the whisper matches the prediction. Another way Quipu can warp our view is through motion. Large concentrations of mass pull on galaxies. They contribute to what astronomers call peculiar velocities. That phrase sounds as if the galaxies are behaving oddly at a dinner party, but it has a specific meaning. In an expanding universe, galaxies generally move away from each other as space expands. The farther a galaxy is, the faster it appears to recede on average. This is the Hubble flow. But galaxies also have local motions caused by gravitational pulls from nearby structures. These extra motions are peculiar velocities. They are motions relative to the smooth expansion. If a galaxy is being pulled toward a massive concentration of matter, its observed motion may differ slightly from what pure cosmic expansion would predict. That matters because astronomers often use redshift, the stretching of light, to estimate distance and expansion. If part of a galaxy's redshift comes from its local motion rather than from the expansion of space, the interpretation becomes more complicated. In nearby regions especially, these peculiar velocities can be significant. The local universe is not a perfectly smooth flow. It has currents, eddies, and streams shaped by the gravitational pull of clusters, superclusters, and large structures. Quipu, along with other nearby superstructures, belongs to that gravitational landscape. It may contribute to large-scale streaming motions in its region. These motions can influence measurements related to the Hubble constant, which describes how fast the universe is expanding today. The Hubble constant is one of the most important numbers in cosmology, and also one of the most debated, because different methods have produced results that do not agree as neatly as scientists would like. Local mass concentrations do not solve the entire Hubble tension by themselves, but they can affect local measurements at the percent level in certain contexts. When precision matters, a percent is not small enough to ignore. This is where Quipu becomes practical. It is easy to admire it as the largest known structure and leave it there, like a cosmic trophy on a very large shelf. But astronomers need to know these structures because they affect the measurements used to understand the whole universe. If the nearby universe contains major mass concentrations, then the local expansion flow may not perfectly represent the cosmic average. If light from distant sources passes through large foreground structures, then the images and signals may be subtly altered. If CMB photons cross evolving superstructures, then the temperature map may carry a small imprint. In every case, the local cosmic landscape becomes part of the measurement. There is a nice earthly comparison here. Imagine trying to measure the true level of the sea while standing in a harbour, with waves, tides, boats, and someone nearby making unnecessary splashes. The sea has a global level, but your local measurement is affected by local conditions. You can still measure it, but you need to account for those conditions. Cosmology has a similar problem. The universe has broad properties, but we measure them from one location, inside one galaxy, within a local cosmic environment that includes clusters, voids, filaments, and superstructures. Quipu is one of the large features in that environment. To measure the cosmic ocean well, we need to understand the local harbour. This does not mean Quipu ruins our view. That would be too dramatic. It refines our view. It reminds us that the universe is not a perfectly smooth background behind a few isolated objects. It has layers. Foreground structures affect background light. Local motions affect redshifts. Dense regions affect galaxy environments. Empty regions affect the contrast of the web. Every observation arrives after passing through the real, uneven universe. The better we map that unevenness, the more accurately we can interpret what we see. There is also a psychological side to this, a softer one. Quipu warps our view not only through gravity and measurement, but through perspective. Before we know about structures like this, the universe may feel like a place made mainly of galaxies scattered across darkness. After Quipu, the darkness begins to feel structured. the galaxies are not simply points. They are part of long, connected forms. The space between them is not just absence, it is part of the web. The largest things are not always bright or obvious. Sometimes they are patterns too large to see until the map is built. That change in perspective is one of astronomy's quiet gifts. It repeatedly shows us that what seems empty or simple is often full of structure when viewed correctly. The night sky looks like stars. A telescope reveals galaxies. A redshift survey reveals filaments and voids. An X-ray cluster map reveals superstructures like Quipu. Each new layer does not cancel the previous one. It adds depth. The stars are still stars. The galaxies are still galaxies. But now they sit inside a larger pattern, and the larger pattern affects how we understand them. Quipu also makes us more aware of selection and viewpoint. We observe from inside the Milky Way, through the dust and stars of our own galaxy. Some directions are harder to study because the Milky Way blocks the view. This means even our map of the nearby universe is shaped by where we are and what lies in front of us. The zone of avoidance is a reminder that the universe does not present itself to us as a perfect survey grid. Our own galaxy gets in the way. Our instruments have limits. Our catalogues have selection effects. Finding Quipu required methods that could work across most of the sky and account for difficult regions. Understanding its full influence requires still better maps. That is important because a superstructure's effects depend on its mass distribution, not just how long it is, but where the mass is concentrated, how dense the clusters are, how the filaments connect, how far the surrounding overdensity extends, and how it relates to nearby structures. For gravitational lensing, the detailed mass distribution matters. For the integrated Sachs-Wolf effect, the evolving gravitational potential matters. For galaxy motions and Hubble flow distortions, the direction and strength of gravitational pulls matter. A rough map tells us Quipu is significant. A better map tells us exactly how significant. This is why future observations are valuable. Better galaxy redshift surveys, improved X-ray cluster catalogues, deeper surveys through obscured regions, weak lensing maps, and comparisons with simulations can all sharpen the picture. Quipu is not simply a finished entry in a list. It is a structure to be studied. Its discovery opens questions about its exact boundaries, its relation to neighbouring superstructures, its full mass distribution, and its observational imprints. A name is only the beginning. Once a structure is named, researchers can ask more precise questions about what it does. The idea of Quipu warping our view also connects to dark matter, because much of the mass responsible for these effects is not directly visible. The galaxies and hot gas show us where some matter is, but dark matter supplies a large share of the gravitational influence. When light bends, when galaxies move, when the CMB is subtly affected, gravity is responding to the total mass, not only to what shines. In this sense, Quipu's observational effects are also clues about invisible matter. The structure is seen through clusters, but its deeper influence comes from the full mass distribution. The universe often lets us study the unseen by watching what it does to the seen. This can be a calming thought if we take it slowly. Not everything important is bright. Not everything that shapes the view is obvious. Some of the largest influences are quiet, spread out, and indirect. Quipu does not glow as one object across the sky, yet it may bend light, affect motions, and leave tiny marks on ancient radiation. Its presence is known through patterns, not through spectacle. The universe is very good at subtlety when it wants to be, which is both beautiful and slightly inconvenient for anyone trying to finish a data analysis before dinner. For the listener resting here, the practical details can be held in a simple way. Quipu is so large and massive that astronomers cannot treat the nearby universe as if it were empty foreground. Its gravity can slightly alter the path of light. Its mass distribution can influence how galaxies move. Its evolving gravitational potential can leave a small imprint on the cosmic microwave background. Its presence must be considered when testing cosmological models and making precise measurements. It does not overturn everything. It does not make the universe unknowable. It simply reminds us that accurate seeing requires accurate mapping. That is perhaps the heart of this part of the story. Seeing the universe is not passive. Light reaches us, yes, but interpretation takes work. A telescope detects a signal. A catalogue records a cluster. A survey measures redshifts. A model accounts for gravity, expansion, and foreground structure. A map reveals Quipu. Then Quipu itself becomes part of the model needed to understand other signals. The observer and the observed are connected by the path light takes through the real universe. No observation floats free of context. As your mind settles into that idea, Quipu becomes less like an obstacle and more like a lens in the broadest sense. It focuses our attention on the fact that the universe is layered. Ancient light from the CMB passes through newer structures. Distant galaxies are seen through nearer mass concentrations. Local galaxy motions sit on top of cosmic expansion. A nearby superstructure tells us about dark matter, gravity, galaxy environments, and the limits of precision measurement. It warps our view, but it also improves our understanding once we know it is there. By now, Quipu has become less like a distant headline and more like a working piece of the universe. It is not just big. It is not just long. It is not just a chain of galaxy clusters with a memorable name borrowed from ancient knotted cords. It is a clue. A very large clue, admittedly. The kind of clue that would not fit on a detective's corkboard unless the corkboard was several 100 million light years across, but a clue all the same. Quipu tells us something about the invisible matter that helped build the cosmic web, and about the gravity that turned tiny early unevenness into galaxies, clusters, filaments, voids, and finally enormous superstructures. To see why, we need to remember what Quipu is made from in the observational sense. Astronomers traced it using galaxy clusters seen in X-rays. These clusters are not small decorations sprinkled along a dark background. They are some of the most massive settled structures in the universe. Each one contains galaxies, very hot gas, and a large amount of dark matter. The hot gas shines in X-rays because it has been heated to extreme temperatures inside the cluster's gravitational field. That X-ray glow is useful because it marks where deep wells of gravity exist. If a cluster is glowing strongly in X-rays, it usually means matter has gathered there in serious quantities. The galaxies are visible, the hot gas is detectable, the dark matter is invisible, but its gravity is holding much of the whole system together. This is where Quipu becomes a guide to dark matter. We cannot see dark matter directly. It does not shine. It does not reflect light. It does not make a nice glowing outline for our convenience, which is understandable, but still a bit inconsiderate. We know it is there because of what it does. Galaxies rotate in ways that require more mass than their visible stars can provide. Galaxy clusters hold together and bend light as if they contain far more matter than we can see. The cosmic web itself has a shape that fits a universe where invisible matter provides much of the gravitational scaffolding. Dark matter is not an extra decoration added to the universe after the fact. It is part of the reason large structures formed in the first place. In the early universe, ordinary matter and dark matter did not behave in exactly the same way. Ordinary matter interacted with radiation. It was pushed, heated, slowed, and coupled to light in the young hot universe. Dark matter, as far as we can tell, did not interact with light in the same way. It mostly responded to gravity. This allowed dark matter to begin gathering into broad gravitational patterns, forming the invisible framework that later helped ordinary matter collect into galaxies and clusters. You can think of it as the first rough outline of the cosmic map. Not a map drawn in ink, but a map drawn in gravity. When the universe cooled enough for ordinary matter to fall more freely into those dark matter wells, the visible structure began to grow. Gas collected where gravity was stronger. Stars formed inside galaxies. Galaxies gathered into groups and clusters. Clusters formed at the densest knots of the cosmic web. filaments stretched between those knots. The result, after billions of years, was the large-scale universe we map today. Quipu is one of the most dramatic nearby examples of that process. It is not just a collection of bright things. It is the visible trace of a much deeper dark matter arrangement. Gravity is the patient worker in this story. It starts with almost nothing, just tiny density differences, and given enough time builds extraordinary structure. A region with slightly more matter than average pulls a little harder. Matter nearby drifts toward it. The region becomes denser. Its gravity grows stronger. More matter arrives. This process repeats, not for years or centuries, but for billions of years. It is slow by human standards, but gravity is not troubled by slow progress. It does not sigh at the calendar. It does not abandon the project halfway through and decide to reorganize a cupboard instead. It continues steadily shaping matter across scales far beyond ordinary experience. Quipu reveals what gravity can do when it works on the largest useful maps of the nearby universe. A single star shows gravity pulling gas into a hot, dense sphere. A galaxy shows gravity organizing billions of stars, gas, and dark matter into a larger system. A galaxy cluster shows gravity gathering many galaxies into a shared environment. Quipu shows gravity shaping not one bound object, but a whole region of the cosmic web, where clusters and filaments form an extended overdensity. Each level teaches us something different. Quipu teaches us about gravity as a builder of patterns, not only objects. That distinction is important. The gravity inside a galaxy cluster can hold the cluster together as a bound system. The gravity associated with Quipu is spread across an enormous region, and does not necessarily make the whole superstructure behave as one single bound object. Parts of the structure may be bound locally, while the full pattern exists as an extended feature in the expanding universe. This means Quipu helps us understand gravity in a more layered way. Gravity can make compact systems, and it can also guide matter into long-connected arrangements that are real, but not solid, real but not neat, real but not easy to draw with a sharp border. Dark matter helps explain why the web has this shape. If the universe contained only ordinary matter, structure formation would have followed a different path. The early interaction between ordinary matter and radiation would have slowed the growth of structure before the universe became transparent. Dark matter gave gravity a head start. It created wells into which ordinary matter could later fall. Without dark matter, the universe would not have grown galaxies and clusters in the same way or on the same schedule. Quipu, by existing as such a massive superstructure, is another sign that the universe's structure depends on a large invisible component. This does not mean Quipu tells us exactly what dark matter is. That question remains open. Dark matter could be made of particles we have not yet detected directly. It might involve physics beyond the standard particles we know. Scientists have searched for it in laboratories, particle detectors, underground experiments, and astronomical observations. So far, dark matter remains known mainly through gravity. Quipu does not solve that mystery by itself. It does not hand us a little label saying dark matter is this, please update the textbooks. But it gives astronomers a huge natural test case for how dark matter behaves on large scales. The way clusters are arranged, the way filaments connect them, and the way the structure compares with simulations all help test whether our dark matter-based model of cosmic growth is working. That model is often called lambda CDM. Lambda refers to dark energy, the component associated with the accelerated expansion of the universe. CDM stands for cold dark matter. Cold, in this context, does not mean dark matter is chilly in the way leftover soup is chilly. It means the dark matter particles move relatively slowly compared with the speed of light, allowing structure to form from small to large over time. In this model, small dark matter halos form first, then merge and grow into larger halos. Galaxies form inside halos. Clusters form from many halos and matter falling together. filaments and superstructures emerge as part of the larger network. Quipu matters because it can be compared with simulations based on this model. Scientists can create simulated universes on computers, starting with early conditions like the tiny fluctuations seen in the cosmic microwave background. They let gravity act. They include dark matter, ordinary matter, cosmic expansion, and dark energy. Then they ask what kinds of structures appear. Do galaxy clusters form in the right numbers? Do filaments appear? Are voids the right size? Do superstructures as large as Quipu happen naturally, or are they too rare to explain? In the Quipu study, the researchers found similar superstructures in simulations based on lambda CDM. That is important because it means Quipu is astonishing but not obviously impossible within the standard picture. There is something reassuring about that. The universe can surprise us without overturning everything. Quipu is not necessarily a crack in the wall of cosmology. It may be a tall mark on the growth chart. It says, under the known rules, gravity and dark matter can build something this enormous. That does not make the structure ordinary. It makes the rules more impressive. A recipe that can produce a small biscuit and a wedding cake is more flexible than it first appears, though the universe's recipe has fewer instructions about oven temperature and more about density fluctuations. Still, astronomers do not simply relax and say, well, that settles it. A structure like Quipu is valuable because it invites more precise tests. How common should such superstructures be? How massive should they be? How connected should the clusters appear? How much galaxy overdensity should surround them? How do they affect local motions and background light? Each question gives researchers another way to compare the observed universe with the simulated one. Dark matter is invisible, but its fingerprints are everywhere in these comparisons. One of the strongest fingerprints comes from gravitational lensing. Mass bends light. It does not matter whether the mass is in stars, gas, black holes, planets, or dark matter. Light responds to the total gravitational field. This is why lensing is such a powerful tool. It lets astronomers map mass without needing the mass to shine. If background galaxies appear slightly distorted in a consistent pattern, foreground mass is probably bending their light. If the bending is stronger than visible matter can explain, dark matter is part of the answer. For galaxy clusters, lensing often reveals enormous dark matter halos extending beyond the visible galaxies. For a superstructure like Quipu, the lensing effect is broader and more subtle than the dramatic arcs produced by individual clusters. The mass is spread across a huge region. The clusters inside it can act as stronger local lenses, while the overall structure contributes to a large-scale lensing field. This is not something a person can see by looking up. It is measured statistically by comparing many faint galaxy shapes and understanding how foreground mass alters them. In that sense, Quipu offers a huge natural laboratory for the relationship between visible traces and total mass. The X-ray clusters show one view, the galaxies show another. Lensing, where available, can reveal the underlying gravitational mass more directly. Quipu also reveals something about gravity's reach. Gravity weakens with distance, but it never simply stops. On local scales it binds objects, on larger scales it shapes flows. Across cosmic time, it turns tiny differences into major structures. A superstructure hundreds of megaparsecs long shows that gravity can organize matter into recognizable patterns over immense regions, even while the expansion of the universe stretches space. This balance between gravity and expansion is central to cosmology. If gravity were much stronger, structures might grow differently. If dark energy dominated earlier or more strongly, large structures might be less developed. Quipu exists in the middle of that balance, as a record of what gravity has managed to build before expansion pulls ever harder on the larger scales. That balance also affects Quipu's future. The dense clusters inside it may remain bound. Smaller groups may continue falling into clusters. Filaments may continue feeding matter into dense regions for a time. but the entire superstructure is not guaranteed to collapse into one object. The expansion of the universe, especially under the influence of dark energy, means many very large patterns may eventually become more isolated or less dynamically connected. Quipu is therefore a present-day feature of the cosmic web, a snapshot of structure formation at this stage in cosmic history. It shows us what gravity has built so far, not necessarily what will remain connected forever. This makes Quipu a kind of time record. Not a clock with hands, but a record of growth. Its clusters, filaments, and mass distribution carry information about the history of matter gathering. The structure tells us that certain regions of the nearby universe became dense enough to form many clusters along a connected arrangement. It tells us that dark matter halos grew, merged, and lined up along the web. It tells us that ordinary matter fell into those wells and became visible through galaxies and hot gas. When astronomers study Quipu, they are not only asking what is there now, they are asking how the universe arrived at this arrangement. The hot gas inside clusters adds another clue. In massive clusters, gas is heated as it falls into deep gravitational wells. The X-rays from that gas help reveal the cluster's mass and state. Clusters are sometimes described as useful cosmological probes because their abundance and mass distribution depend on how structure grows over time. A universe with different dark matter behavior or different gravity might produce a different population of clusters. Since Quipu is traced by clusters, its structure is connected to the same questions. The number of clusters, their masses, their locations, and their connection to surrounding galaxy overdensities all help test the growth of structure. There is also the environmental side. Dark matter does not only shape where clusters are, it shapes the pathways galaxies take before reaching those clusters. A galaxy may form in a smaller dark matter halo, join a group, travel along a filament, and eventually enter a cluster. Along the way, its gas supply, star formation, and shape may change. The web is not only a static skeleton, it is a set of roots. Quipu, as a large piece of that web, helps astronomers study how environment influences galaxies across a huge range of density. Dense cluster core, cluster outskirts, filament, side branch, lower density surroundings. Each environment tells a different part of the gravity and dark matter story. Because Quipu is so massive, it also connects to the question of cosmic flows. Matter does not just sit in place while the universe expands. Galaxies have motions caused by gravity from nearby mass concentrations. These peculiar velocities can help reveal where mass is concentrated, including mass we cannot see. If galaxies stream toward a region, that motion hints at a gravitational pull. Large superstructures contribute to these flows. Quipu's mass distribution may therefore matter for understanding motions in the nearby universe. Again, the visible structure points toward the invisible gravity underneath. The same applies to the cosmic microwave background. As ancient light travels through evolving gravitational fields, large structures can leave subtle imprints, such as through the integrated Sachs-Wolf effect. This effect is linked to the changing gravitational potentials of large-scale structures in an expanding universe influenced by dark energy. Quipu is large enough that it may contribute to such a signal, though detecting it clearly is difficult. The fact that researchers even look for these imprints shows how seriously large structures are taken. A superstructure is not just a map feature. It can become part of the evidence chain linking gravity, dark matter, dark energy, and cosmic expansion. In a calm, practical sense, Quipu reveals that our current picture of dark matter and gravity is powerful. It can explain enormous structures without needing every discovery to become a crisis. But it also reveals where the picture needs constant testing. Simulations must match observations. Cluster maps must be checked against galaxy surveys. Lensing must be compared with visible matter. Motions must be understood. CMB imprints must be searched for carefully. The larger the structure, the more useful it becomes as a test, because small errors in our understanding can become noticeable at large scales. This is one of the reasons astronomy often feels like a conversation between the visible and the invisible. We see galaxies, but infer dark matter. We detect X-rays, but infer deep gravitational wells. We measure redshifts, but infer distances and motions. We map clusters, but infer the cosmic web. We observe Quipu, but what it reveals most strongly is not just the matter that shines. It reveals the hidden gravitational architecture that made the shining matter gather there in the first place. That architecture is not a vague idea. It has concrete effects. It affects where galaxies form. It affects how clusters grow. It affects how light bends. It affects how matter moves. It affects what simulations must reproduce. Dark matter may be invisible to telescopes, but it is not invisible to the structure of the universe. Quipu is part of that structure, and therefore part of the evidence. It is like seeing the outline of a submerged reef by watching how waves break above it. The reef is not directly visible from the surface, but the water gives it away. In the same way, galaxies and clusters give away the dark matter landscape beneath them. Gravity, meanwhile, is the rule that makes the clue readable. Without gravity, dark matter would not scaffold the web. Ordinary matter would not fall into halos. Gas would not heat in clusters. Light would not bend around mass. Galaxies would not stream toward overdensities. Gravity is not just another force in the background of this story. It is the grammar of the cosmic sentence. Quipu is one of the longest sentences we have found nearby, written in clusters, filaments, and voids. And yet, for all that scale, the lesson can be held simply. Quipu shows that the universe is shaped by more matter than we can see, and by gravity acting over more time than we can easily imagine. It confirms that the biggest visible structures are only the bright surfaces of deeper mass patterns. It gives astronomers a huge nearby example to compare with simulations, lensing, galaxy surveys, and motion studies. It does not tell us everything about dark matter, but it tells us where dark matter has been working. It does not change the law of gravity, but it shows the law operating across a region so large that the result feels almost unreal. If dark matter and gravity can produce Quipu, then the next question is hard to avoid. Is Quipu truly the largest structure the universe has made, or only the largest one we have found so far? That difference matters. The universe is not required to show us its record book in order. It does not place the biggest thing in the easiest part of the sky, with a neat arrow beside it and a small note saying, "Start here." Astronomy usually works the other way around. We find what our instruments are able to reveal, inside the limits of our surveys, our methods, our definitions, and our position inside the Milky Way. So when we say Quipu is the largest structure ever found, the safest and most honest meaning is that it is the largest cosmic superstructure reliably identified in this way, with this kind of mapping, in this region of the nearby universe. That still makes it extraordinary. It does not make Quipu any less impressive. A structure more than 1 billion light-years long does not become ordinary just because the universe might be hiding something larger elsewhere. If anything, that possibility makes the story wider. Quipu becomes not only a record holder, but a hint. It tells us that the cosmic web is capable of producing enormous connected patterns. It shows that galaxy clusters can trace structures much larger than ordinary galaxy clusters, or even familiar superclusters. And once we know that one such structure exists, it becomes natural to ask whether other chords, walls, arcs, or filaments are waiting in the data, not yet fully mapped, not yet named, perhaps partly hidden behind dust or distance. The first reason larger structures might be waiting is simple. We have not mapped the entire universe with equal detail. That may sound obvious, but it is easy to forget. Maps of the cosmos are not like finished wall maps in a classroom, where every country has a border and every ocean has been coloured in. Cosmic maps are built through observation, and observation has limits. Some surveys look deeply into a narrow region. Others cover much of the sky, but only to certain distances or with certain kinds of objects. Some are excellent at finding galaxies. Some are better at finding galaxy clusters. Some use X-rays, some visible light, some infrared light, some radio waves, some gravitational effects. Each survey gives a different kind of map, and no single map shows everything perfectly. Quipu was found using X-ray galaxy clusters, which are excellent tracers of the densest knots in the cosmic web. That method is powerful because galaxy clusters mark deep gravitational wells. They are massive, important, and useful for mapping large-scale structure. But a cluster-based map naturally emphasizes the places where clusters are present. Other parts of the web, such as fainter filaments with fewer massive clusters, may require different methods to trace well. A structure could be large but not rich in X-ray bright clusters. Another could be distant enough that its clusters are harder to detect. Another could lie in a region where our view is partly blocked. The universe has many ways to be inconvenient without even trying. One of the biggest inconveniences is our own galaxy. The Milky Way is home, which is lovely, but it also gets in the way. Its disk contains stars, gas and dust, and when we look through that crowded plane, distant galaxies and clusters become harder to see. Astronomers call this region the zone of avoidance, which sounds like a place where a sleepy traveller should absolutely not leave the path after dark. In reality, it is a region of the sky where our view of the extragalactic universe is obscured. There may be large structures partly hidden behind it, or structures whose connections are harder to trace because part of the map is missing. Quipu itself reaches toward regions where the Milky Way's foreground complicates the view. That means even with a very strong detection, the full surrounding cosmic landscape may still have hidden pieces. This is one reason future surveys matter so much. Infrared observations can see through dust better than visible light. Radio surveys can detect neutral hydrogen in galaxies even in difficult regions. X-ray surveys can find hot gas in galaxy clusters. Gravitational lensing can reveal mass whether or not it shines. Each method opens a different window. As these windows improve, astronomers may find that known structures connect farther than expected, or that separate structures are part of a broader arrangement, or that entirely new superstructures sit where older maps were incomplete. There is a delicate balance here, though. It is tempting to join everything together. Once you start seeing filaments and connections, the universe can begin to look like one enormous network, because in a broad sense, it is. But not every nearby cluster belongs to the same named structure. Astronomers need careful rules. They must decide how close clusters need to be to count as connected. They must measure whether a region is truly overdense compared with the background. They must check whether a pattern is real in 3 dimensions or only appears connected from our viewpoint. They must avoid drawing a cosmic dinosaur in the clouds just because the dots look exciting at 2 a.m. after too much coffee. This is why the question of larger structures is not only about finding longer chains. It is about finding structures that remain meaningful under careful analysis. A claimed structure must be supported by data. Its members need reliable distances. Its density needs to be higher than expected. Its shape should not be a chance projection. Its existence should hold up when selection effects and survey limits are considered. This is especially important for very large structures, because the larger the claimed size, the more carefully astronomers must ask whether the structure is physically meaningful or just a statistical pattern. There have been other enormous candidates in the history of cosmic mapping. Some have been traced through galaxies, quasars, or gamma-ray bursts. You may hear names like the Sloan Great Wall, the Giant Arc, the Big Ring, or the Hercules Corona Borealis Great Wall. These names sound wonderfully dramatic, as if the universe has been quietly building monuments and waiting for someone to notice. Some of these structures are very interesting. Some are still debated. Some depend on traces that are sparse or difficult to interpret. Gamma-ray bursts, for example, are brilliant events, but they are rare, and using them to trace very large structure requires careful statistics. A giant pattern suggested by a small number of rare events is intriguing, but it needs confirmation from more data and other methods. Quipu's strength is that it was identified in the nearby universe using galaxy clusters from an all-sky X-ray based survey. That makes it a comparatively solid kind of structure for this scale. It is still not a solid object, and its boundaries still depend on definitions, but the evidence is grounded in known cluster positions and distances. Larger candidate structures may exist, especially farther away, but the confidence level can vary. This is why astronomy often distinguishes between the largest known reliable structure and the largest claimed or possible structure. The universe may allow both statements to appear in different conversations, which is not confusing at all, except that it absolutely is. There is another reason larger structures may be waiting. The observable universe is enormous, and we occupy only one point within it. Even if structures as large as Quipu are rare things can appear somewhere in a volume this vast. Imagine searching a huge beach for unusually large shells. If you examine only one patch carefully, you may find the largest shell in that patch. It may be impressive. It may be the largest shell you've ever seen. But the beach continues beyond your search area. There may be larger shells farther away, partly buried, or hidden near rocks. The sensible response is not to doubt the shell you found. It is to keep mapping. Cosmic surveys are doing exactly that. They are becoming deeper, wider, and more detailed. New galaxy redshift surveys are measuring the distances to millions of galaxies. X-ray missions continue to improve cluster catalogues. Radio telescopes are opening hidden regions. Weak lensing studies are mapping mass directly through the subtle bending of light. Each improvement helps reveal more of the cosmic web. The more complete the web becomes, the more likely it is that astronomers will identify new giant features. Some may be smaller than Quipu, some may be comparable, a few may be larger. Yet there may also be a practical limit to how large a meaningful structure can be. This is connected to one of the major assumptions in cosmology, often called the cosmological principle. On sufficiently large scales, the universe should be roughly homogeneous and isotropic. Homogeneous means matter is distributed similarly from place to place, when averaged over very large volumes. Isotropic means the universe looks broadly the same in all directions, again when viewed on large enough scales. This does not mean the universe is smooth everywhere. Clearly it is not. There are planets, stars, galaxies, clusters, filaments, voids, and Quipu. But if you zoom out far enough, the clumps and gaps should average out. Very large structures test this idea. If we found a structure so enormous that it could not fit within the expected level of cosmic lumpiness, that would be a serious challenge. It might mean our understanding of structure formation needs revision, or that the claimed structure is not a single physical feature, or that the statistics are being affected by selection bias. This is why record-breaking structures are treated with both excitement and caution. They are thrilling because they push the limits. They are examined carefully because the limits matter. Quipu appears to fit within current expectations because simulations based on the standard cosmological model can produce similar superstructures. That is important. It suggests that something Quipu-sized can arise naturally from dark matter, gravity, cosmic expansion, and the initial conditions of the universe. If something even larger is found, scientists will ask the same question. Can simulations produce it? How often? Under what conditions? Is it truly one connected structure or a chance alignment? Does it trace real mass, or only a sparse set of objects that happen to line up? The answer would determine whether the discovery is a new landmark within the model or a sign that the model needs adjustment. The definition of structure becomes very important here. A galaxy cluster is a physical system with a strong gravitational identity. A superstructure is broader. It is connected over density, but not necessarily one bound object. At very large scales, the boundary between one structure and the surrounding web becomes harder to define. The cosmic web is continuous. Filaments connect to clusters. Clusters connect to other filaments. Walls border voids, and neighbouring overdensities may blend together. If the linking rules are too generous, almost everything can become connected to everything else. If they are too strict, real large structures can be split into smaller pieces. Finding larger structures therefore requires not just better data, but careful definitions. This makes the possibility of larger structures both exciting and complicated. There may indeed be longer filaments or broader walls. There may be superstructures that extend beyond current survey limits. There may be hidden connections through the zone of avoidance. There may be distant patterns revealed by future redshift surveys or by better maps of quasars and gamma-ray bursts. But each possible discovery has to pass through the same careful questions. Is the structure real in 3 dimensions? Does it correspond to an overdensity of matter? Is it statistically significant? Does it appear in more than one kind of data? Can it be reproduced or explained by simulations? The universe is allowed to be grand, but science asks it to show its receipts. There is also a difference between looking nearby and looking far away. Quipu is in the nearby universe by cosmological standards. That makes it easier to map in detail than many more distant structures. Farther away, light has taken longer to reach us, so we are seeing the universe at an earlier time. Objects are fainter. Distances can be harder to measure. Surveys become less complete. Large claimed structures at great distances may be harder to verify, because the traces are sparse, or because the universe itself looked different at that time. That does not mean distant giant structures are impossible. It means they require extra care. As instruments improve, astronomers will be able to test these distant patterns more strongly. Future surveys may map more galaxies and quasars across larger volumes. They may improve redshift precision. They may detect more clusters at greater distances. They may reveal the warm gas in filaments more clearly. They may use weak lensing to map the dark matter web directly over wide areas. With each step, the question, could something larger be out there, becomes less like speculation and more like an observational program. We do not have to guess forever. We can keep looking. Still, even if a larger structure is eventually found, Quipu will remain important. Record holders change. Scientific value does not vanish just because a new record appears. The Milky Way did not stop mattering when we learned there were other galaxies. The solar system did not become uninteresting when exoplanets were found. Quipu would still be a major nearby superstructure, a massive feature in our cosmic environment, and a key example of how galaxy clusters trace the web. If someday astronomers find a larger chord, wall, or arc, Quipu will become part of the path that led there. It will be one of the structures that taught us what to look for. That is a useful way to think about all record-breaking discoveries. The title is exciting, but the lesson is deeper. The largest known structure is not important only because it is largest. It is important because it reveals what the universe can build, what our methods can detect, and what questions we should ask next. Quipu tells astronomers that X-ray cluster mapping can uncover enormous nearby superstructures. It shows that the local cosmic web contains major features that can affect precision measurements. It offers a comparison point for simulations. It gives researchers a target for follow-up studies, and it invites the search for more. There is a gentle humility in that. Every map is provisional. Every record is current only until the next careful discovery. Astronomy is full of phrases like known so far, currently measured, best estimate, candidate, likely, and pending confirmation. Those phrases are not weakness. They are how science stays honest while looking into a universe that is larger than any one survey. Quipu is not diminished by that honesty. It becomes more interesting because it sits at the edge of what we have mapped well. For a sleepy mind, the possibility of larger structures can be held in a calm way. Somewhere beyond the current catalogues, there may be longer filaments. Somewhere behind the Milky Way's dusty plain, There may be connections we have not traced. Somewhere in distant surveys, a pattern of galaxies or bursts may be waiting for enough data to confirm it. The universe may have tied other knots in the dark, knots we cannot yet read. But we are learning the language. Cluster by cluster, redshift by redshift, photon by photon, the map becomes clearer. And perhaps the most surprising part is that larger structures, if they exist, may not look dramatic when first seen. They may appear as statistical patterns. A slight excess of galaxies here, a chain of clusters there, a set of redshifts that gather more than expected, a faint lensing signal, a hidden overdensity behind foreground dust. The largest things in the universe may arrive quietly, as data points becoming a shape. That is how Quipu entered the story, not as a glowing object in one telescope image, but as a long arrangement revealed by patient mapping. So yes, larger structures could be waiting out there. The answer is not only possible, but almost expected in the broad sense that our maps are incomplete, and the observable universe is vast. Whether any of them will be as reliably characterized as Quipu, or even larger in a way that holds up under careful testing, is a question for future surveys. The universe may have more record holders hidden in its web. It may also teach us that some dramatic candidates fade under better data, while quieter, better mapped structures become the ones we trust. Both outcomes are useful, both make the map better. For now, Quipu stands as a remarkable marker of what has been found. A huge nearby superstructure, traced by galaxy clusters, shaped by dark matter and gravity, large enough to influence how we interpret the cosmos. It is not necessarily the final answer to cosmic size. It is a milestone. After travelling through the discovery, the scale, the clusters, the filaments, the voids, the dark matter, and the quiet pull of gravity, we finally arrive at the part of the story that is hardest to measure, but easiest to feel. Quipu is not only a large structure in space. It is also a reminder of where we are, not in the dramatic sense of a map pin that says, "You are here," although that would be useful if the universe ever decided to install signs. It is a reminder that our home is part of a vast connected arrangement of matter, one that stretches far beyond galaxies, far beyond clusters, and far beyond the limits of ordinary imagination. We live inside a universe that is not random clutter, not smooth emptiness, not a dark stage with a few bright actors scattered around, but a web. That word, web, has followed us for a reason. It is the best simple image we have for the way matter gathers on the larger scales. Galaxies are not sprinkled evenly through space. They gather into groups, clusters, filaments, walls, and superstructures, with huge voids lying between them. The result is not tidy, but it is organized. It is not designed, but it has structure. It is not alive, but it has grown. And somewhere inside that web, on a small rocky planet orbiting an ordinary star inside the Milky Way, there is you, listening from a room, a bed, a sofa, a train seat, a quiet kitchen, or wherever your little pocket of the universe happens to be tonight. That contrast is worth sitting with for a moment. Quipu may be around 1.4 billion light-years long. Earth is about 12,742 kilometers wide. A human life is measured in years, perhaps decades if we are lucky. A galaxy cluster evolves over billions of years. A kettle boils in minutes. A star forms over hundreds of thousands or millions of years. A message can arrive in a second and somehow still feel too much to answer. These scales do not match neatly. They were never meant to. The universe contains them all anyway. This is one of the quiet meanings of living inside a cosmic web. We are small but not separate. Smallness often sounds like a sad idea when people talk about space. They say we are tiny compared with the universe, and of course, physically that is true. We are tiny compared with a planet, a star, a galaxy, a cluster, and certainly compared with Quipu. But tiny is not the same as disconnected. A single cell is tiny compared with a body, but it belongs to the body. A single house is tiny compared with a city, but it belongs to the city. A single word is tiny compared with a book, but it helps make the book readable. Earth is small, but it belongs to the cosmic web. So do we. That does not mean the universe was arranged for us. It does not mean Quipu formed with any awareness that one day sleepy humans would give it a name and try to imagine it before bed. The cosmic web formed through physical processes. Gravity acted on tiny early density differences. Dark matter shaped the scaffolding. Ordinary matter collected into galaxies and clusters. Voids opened as matter drained toward denser regions. Filaments stretched between the knots. None of this required human meaning, but human beings are meaning-making creatures. We look at the structure and ask what it tells us about our place inside it. One answer is that place is layered. You are not only in a room, you are on Earth. Earth orbits the Sun. The Sun sits inside the Milky Way. The Milky Way belongs to the local group. The local group is part of a larger cosmic environment shaped by nearby clusters, filaments, voids, and flows. Beyond that, the web continues. Somewhere in the broader nearby universe lies Quipu, one of the largest mapped arrangements of galaxy clusters ever found. Our address is not a single line. It is a stack of belonging, each layer larger than the last, until ordinary language begins to creak under the weight of distance. And yet the layers do not erase the smaller ones. Knowing about Quipu does not make your room less real. It does not make the cup beside you less real, or the blanket, or the sound of rain, or the small comfort of turning a pillow to the cooler side. In fact, it can make those things feel stranger and more precious. The same universe that contains billion light-year structures also contains warm lights in windows, quiet conversations, and the little rituals people use to settle themselves at the end of a day. Large and small are not enemies. They are different scales of the same reality. That is something astronomy teaches again and again. When we first learn that Earth is not the centre of the solar system, the world does not become less meaningful. It becomes part of a larger system. When we learn that the Sun is one star among hundreds of billions in the Milky Way, the Sun does not become less important to us. It becomes our star, in a galaxy full of stars. When we learn that the Milky Way is one galaxy among billions, home does not disappear. It becomes more specific, and when we learn that galaxies themselves gather into a cosmic web, our place becomes even more layered. We are not at the centre of everything, but we are inside everything. That is not a bad trade. Quipu also changes the way we picture darkness. In everyday life, darkness often means emptiness. A dark room is one where the light is off. A dark patch of sky may look like nothing is there. But cosmic darkness is not simple absence. Much of the universe is dark because the matter does not shine, or because the light is too faint, too stretched, too distant, or blocked by foreground dust. Dark matter shapes the web without glowing. Voids look empty but define the structure around them. Filaments may be too faint to see directly, yet they connect clusters across vast distances. Darkness, in astronomy, is often full of information. It is just information that requires patience. There is a good lesson in that, not a grand lesson, not something printed on a motivational poster beside a mountain, but a practical one. Not everything important is obvious at first glance. The largest known structures may not appear as bright objects. They may require maps, catalogues, and careful inference. A major part of the universe can be hidden in relationships between things rather than in a single shining thing. Quipu is not seen as one object in the sky. It is recognized through the arrangement of clusters and the matter around them. It exists as pattern, and pattern requires attention. The same is true of the cosmic web as a whole. If you look only at one galaxy, you see one galaxy. If you look at millions of galaxies with distances measured carefully, you see the web. The meaning is not in the dots alone. It is in the arrangement. This is why maps are so powerful. A map does not create the land. but it reveals relationships that were hard to see from the ground. Astronomy is full of such maps: star maps, galaxy maps, cluster maps, dark matter maps, microwave background maps. Each one turns scattered signals into a form the mind can hold. Quipu is one of those forms, a long cord of clusters, a huge superstructure in the nearby universe, a record of gravity's slow work. It gives the mind a shape to rest on, not because the full scale is easy to imagine, but because the shape is simple enough to begin with. Knots on a cord, clusters along a filament, a structure large enough for light to spend more than 1 billion years crossing it. You do not have to picture every galaxy inside it. You do not have to count the clusters in your head like sheep, although if you did, it might be surprisingly effective. You only need to understand that the universe has made patterns larger than galaxies, and we are learning to read them. There is also a kind of comfort in the slow pace of it all. Quipu did not form quickly. The cosmic web did not appear in a hurry. Gravity shaped it across billions of years. The clusters grew slowly. The filaments became more distinct slowly. The voids opened slowly. The structure was there long before humans had telescopes, long before humans existed, long before Earth had anything like the familiar world outside your window. And now, at this particular moment in cosmic history, we have instruments and minds capable of noticing it. That is a remarkable meeting of timescales, a billion-year structure and a human thought, touching briefly through observation. This does not mean the universe is waiting for us to understand it. It simply means that understanding is one of the things the universe has made possible. Stars made heavy elements made rocky planets. On at least one rocky planet, life appeared. Life became aware. Awareness built telescopes. Telescopes mapped clusters. Clusters revealed Quipu. The story is physical all the way down, but it is still astonishing. Matter arranged itself into beings who could study how matter arranged itself. That sentence is almost rude in how strange it is, and perhaps that is the deepest quiet meaning here. The cosmic web is not just outside us. We are made from the same universe that formed it. The atoms in your body were forged in stars and stellar explosions. The calcium in bones, the iron in blood, the carbon in cells, all belong to the long chemical history of the cosmos. You're not made of a different kind of stuff from the universe you're studying. You're not a visitor standing outside the scene. You are a local expression of it. A very small, warm, breathing part of the same matter story that, on larger scales, gathers into galaxies and filaments. That does not make a person the same as a galaxy cluster, which is probably for the best. Galaxy clusters are not known for making tea, texting friends, or wondering if they should really have stayed up for one more video. But it does mean there is continuity. The physics that shape the cosmic web is not unrelated to the physics that allows stars, planets, chemistry, and life. Gravity builds large structures. Electromagnetism allows atoms and chemistry. Nuclear processes power stars. Time allows complexity to unfold. The universe works at many scales, and we inhabit one of them, aware of several others. Living inside a cosmic web also means living inside motion. The structures may look fixed on our time scales, but they are not frozen. Galaxies move, clusters grow, matter flows along filaments, voids become more pronounced. The Milky Way itself moves within the local cosmic environment. Earth moves around the sun moves around the galaxy. The galaxy moves with its group. Nothing is truly still. Even rest happens inside motion. When you lie quietly in bed, feeling still, you're still carried by Earth's rotation, Earth's orbit, the sun's motion through the galaxy, and the galaxy's motion through the broader cosmic flow. Stillness, it turns out, is a local feeling. The universe is always quietly going somewhere. That thought can be surprisingly soothing. You do not have to hold everything in place. Nothing is held perfectly in place. The universe is built from motion, change, and relationship. The cosmic web itself is the result of matter moving in response to gravity over time. It is not a rigid structure. It is a slow process made visible as pattern. We live inside that process. We measure it, name parts of it, and sometimes fall asleep while thinking about it, which is a perfectly respectable form of participation. Quipu also reminds us that our maps are still young. There may be larger structures waiting. There may be hidden connections behind the Milky Way. There may be features that future surveys will reveal with better precision. The universe is not finished being mapped by us, and it may never be finished in any final sense. Each generation of instruments makes the map clearer. Each clearer map changes the questions. A discovery like Quipu is not the end of the story. It is one marker along the path of learning how matter is arranged on the greatest scales. That is another quiet meaning. Knowledge is cumulative, like the structure it studies. One measurement alone may not show the web. Many measurements do. One galaxy alone may not reveal the pattern. Millions of galaxies do. One cluster alone is impressive. Many clusters in relation reveal Quipu. Human understanding grows in a similar way. One observation, one paper, one survey, one correction, one new instrument, one careful comparison with simulations. Slowly the picture becomes less blurry. Science is not always a lightning bolt. Often it is a filament. Maybe that is why Quipu is such a fitting subject for a sleepy journey. It is enormous, but it was found through patience. It is dramatic in scale, but subtle in appearance. It is a record breaker, but not a loud one. It does not explode, collide, or flare. It simply stretches across the nearby universe, traced by clusters, shaped by gravity, waiting for enough data to make its pattern visible. It is a cosmic structure that rewards slow attention. And slow attention is exactly what a tired mind can offer, especially when the day has finally loosened its grip. So, as we think about living inside a cosmic web, perhaps the feeling to keep is not fear or smallness, but orientation. We are located. We are part of a structure. We belong to a layered universe where matter gathers, connects, thins, and gathers again. Around us are planets and stars. Beyond them are galaxies. Beyond them are clusters and filaments. Beyond them are superstructures like Quipu. The web is not something separate from home. It is the larger pattern in which home exists. And home, after all, has always been a layered idea. It can be a room, a person, a routine, a landscape, a planet, a star system, a galaxy. Tonight, we can stretch the idea a little farther and let home include the web itself. Not because we can travel across it, and not because we can see it directly from the window, but because we are physically within the same cosmic arrangement. The night sky above you is not a ceiling. It is the nearest visible surface of a much deeper map. If you're still awake, gently notice where you are. Notice the ordinary scale first, the room, the sound around you, the weight of your body resting, the rhythm of breathing. Then let the scale widen, Earth turning, the moon moving, the planets circling the sun moving through the Milky Way travelling with its neighbours. Galaxies gathering into groups, groups into clusters, clusters into filaments, filaments into great superstructures. Somewhere in that vast web, Quipu stretches like a long knotted record of gravity's patience. And if this journey through one of the largest known structures in the universe has brought you a little calm, or a little wonder, or simply a softer place for your thoughts to land, I would be ever so grateful if you liked the video, subscribed, and shared this quiet corner of science with someone else who might enjoy drifting through the cosmos at a slower pace. The universe is far too large to understand all at once. But we do not need to understand it all tonight. We only need to follow one thread at a time. Quipu began for us as a name, then became a structure, then a map, then a clue, and finally a reminder. The universe is connected. Matter remembers gravity. Darkness can hold structure. Small things can belong to enormous things, and here you are, somewhere inside the web, listening from your own tiny bright knot of experience, held not by cosmic certainty, but by the gentle fact of being here at all. So rest now, fellow traveller, wherever you are in the great pattern, and let the thought of that vast quiet web loosen slowly into sleep,